Namaste. Good morning, everyone. Welcome to the third day of the International Conference on Towards 5G Advanced and 6G organized by DOT and TSTSI. I am Sonia Sachdeva Sharma from TSTSI. I, along with my colleague Shefali Sinha and Anupam Sinha, are your hosts for this conference. I now invite Professor Brajesh Lal from IIT Delhi to take the proceedings forward. Professor Brajesh Lal is presently Professor Electrical Engineering Department and has earlier served as the head of the Bharti School of Telecom Technology and Management at IIT Delhi and the coordinator of two centers of excellence,
Brajesh Lal
IIT Delhi Center of Excellence in Telecommunications and Ericsson IIT Delhi 5G Center of Excellence. He is also the in charge of an IoT laboratory that he set up in collaboration with Samsung. He is also the co-PI of the project Building an End-to-End 5G Testbed funded by DOT. Sir, the floor is yours.
Morning everyone. Welcome to the day 3 of this conference. Today, we are privileged to have with us Mr. Mohan Rao Goli from Samsung. He is going to make the keynote address this morning. The topic of his presentation is 6G vision, megatrends, technologies, and spectrum. Korea, well, actually the Korea perspective would probably be, in general, the perspective that Samsung has beyond Korea as well, I presume. And before I hand over the dais to Mr. Goli, even though he needs no introduction, let me just go through the process of introducing him. So Mr. Mohan Rao Goli, he currently heads the Communications Center of Excellence at Samsung Research India for 5G, 5G advanced standards development and pre-6G research initiatives, as well as 5G device and network advanced solution development. He has earlier spearheaded the global 4G and 5G R&D program for Samsung Mobile business, closely collaborating with ecosystem partners across the world, and contributed significantly to development and communication services such as IMS, RCS, and MCX services. He is also a key proponent of open source development, overseeing contributions to Open RAN development. Mohan holds over 20 patents in communications domain, and his current areas of interests include advancement in next generation communication systems, including AI, ML in wireless, terahertz communications, and cloud native architectures. I welcome you to the presentation. Thank you so much.
Can you put up the slide? Yeah. Thank you. Good morning, everyone, and welcome to the, am I audible? Okay. So it is a kind of notion that in online meetings we always say that audible or not. Okay. So welcome to the day 3 of this International Tech Conference. So today's topic is very close to my heart, and we are doing a lot of work related to the 6G research and defining the vision and defining the closely monitoring the technology trends, and then what kind of technologies will really define the 6G for the future. People may think that, hey, 5G is just launched 2 days back in India, and what is about the 6G? But from the Samsung perspective, we had much experience related to the 5G deployment and research and development and taking into the market as well. So now that the communication engineers is focusing more on the what is going to be the next G is going to come up. It is prevalent that, okay, anyway, I will get into the slides. I will briefly touch upon the evaluation of the 5G and 5G advanced topics, and it will set a stage for the why we need to have the 6G actually. From the 6G visions and requirement and technology and based on Samsung view, I wanted to present today. And the most important thing is that any G is started, there will be a discussion about the spectrum. So the 6G is not exceptional about that. So we are going to talk about the spectrum and what kind of standardization timelines we can see for the 6G point of view. I think most of the last two keynotes by Dr. Durga and Dr. Magnus covered about the 5G and 5G advancements and what kind of applications and requirements the humankind can see it, right? But I will give some brief evaluation what the Gs are happening in wireless communications. As a thumb rule, every 10 years, new G will come actually. I completely agree with Durga. He made this statement in day before yesterday. And I kind of say that 8 years, I was thinking 8 years, but I will go with him, 10 years. Every 10 years, we have a G. But is it like communication engineers' safety to create the Gs, or is it really consumer experience is improving it? I think consumer experience is really improving it. When you come to the 2G case, voice and SMS became the true killer applications for the people to come out from the fixed telephony systems to the mobile communications. And in 3G provide the mobile internet. And 4G created the mobile broadband. And 5G is enhanced the mobile broadband. We are talking about ultra reliability, low latencies communications. And we are also talking about massive machine type communications. So in a way, I could see that wireless communication is becoming like a horizontal platform. All the industries, 5G is much talked about it compared to the other generations. Why? Because there are multiple vertical industries are going to utilize this horizontal platform and leverage the services getting offered by the 5G to realize their automations and their digitalization requirements. If you can see around IMC event, many of the stalls, they are talking about the agricultural, logistics, farming, and smart factories, entertainment, gaming, all these kind of industries are getting benefited with the strong foundation laid by the 5G. So what is to define about the 6G? So that is a question mark, and we are all here to talk about that particular question mark and solve that puzzle. So global 5G snapshot, 2019 is the year where we have seen the dramatic launches of the 5G in North America and Korea, and then followed by Japan, China, and Europe. And India seen the 5G. I'm getting the 5G signals from 2 days back onwards from Airtel. But 200 operators in 78 countries already seen the 5G, and around 520 million 5G mobile subscribers as the first quarter 2022. And 830 million smartphone shipments are happened based on the 5G actually. So this is a small snapshot about the 5G. So it is going to stay here, and major offerings from the 5G has happened so far in the world is enhancing the mobile broadband only. And I hope that the next further deployments and next further releases of the 5G is going to make these vertical industries to flourish more. Few more years is going to happen. These are the 3GPP standards timelines for the 5G and 5G evaluations. Release 15 is the first release where the 5G started showing the commercializations. Both FR1 and FR2, as well as the network slicing, got standardized by release 15. Release 16 got little more enhancements in terms of the UE power consumption, because there is a lot of debate about how to do the UE power consumptions. So there is a wake-up signals and UE-assisted informations, and these kind of procedures got defined in the release 16, and which influences the UE power consumptions. And at the same time, the network analytics and vehicle-to-vehicle signaling has been standardized in the release 16. And current networks and then devices are slowly getting migrated to the release 16 across the world. Release 17, which is first quarter 2022, got standardized, which deals about the public safety and edge computing as well as the network automations procedures. So these are the three major things which are happening in the release 17. But release 18 is taken up one particular step, one really bold step to bring that AI/ML introduction to the wireless communications. If you look at that AI/ML models, powered the visual intelligences, natural language intelligences, natural language understandings, and many aspects the AI/ML models are got into it. AI/ML model also entered into the wireless communications, especially in the beam learning techniques and beam prediction techniques and CSI, channel condition prediction techniques. These are the things where the AI/ML will play a very important role in the 5G evaluation space, which is taken up by the release 18. And of course, the network energy saving and UAV and NTN, these are the topics that will be further dealt in the release 18 standardizations. Yeah, so far everything is good, right? So why do we need 6G? 6G, in our view, I would like to take up the two examples and then let's think about that, right? So if you look at the IMC stalls, I was talking to some people here. Every stall, I can see the XR headsets. AR-related technologies are happening, which is very, very good sign. But my belief is that in 2 to 3 years, the quality, AR visions and XR vision related quality will substantially be very high. So that's where the people will started realizing using this XR related or AR related use cases to be visible. To have the high fidelity XR view or to make the point cloud of the person or the object, we need to have the 500 megabytes per second kind of speeds, which translates to about 4 gigabits per second. I think we need to have that much bandwidth at the communication platform level to have to transfer that much data in real time so that the replica can be generated very, very quickly and then with the high resolution itself. 6G is the only way I think it can go in that path. Second example, I was also talking to some people there that, hey, what would be the device ecosystems when it comes to the 6G area after 10 years, right? Is it going to be the human? See, last few generations of the wireless communications is drastically dealt with the human-related consumer use cases. Humans are having natural limitations. So our field of view with the eye, with certain FPS, certain latencies, only is enough to have the higher quality. But machines doesn't have that kind of limitations. They may be limited by their computing, but computing is getting evolved, right? So with the latest technologies about the computing and latest nanometer technologies and great system software is coming up, the machines may not be having that particular limit. So that would be the basis for the 6G communication to talk about it. It is not just the consumers, where the consumer cannot see. For example, today, the AI-based camera can see the nightography where the human eye cannot see it, right? So that's where the life that we are living in, and that is going to be substantially will improve. So the 6G has to deal with this kind of devices ecosystems and this kind of fundamental, or it may become fundamental requirements for the going forward. So these are the mega trends that are happening towards the 6G thing. First one, like I mentioned, about it's not just the humans. The machines are going to communicate each other. They don't have any limitations except the computing factors actually, but the computing is also is improving it. It is expected that by 2030, there will be 500 billion connected devices, maybe more than 500 billion connected devices will be there. And every human will have, on an average, about 4 to 5 devices within himself. So all these things need to be connected. They have to bring that connected experience to these consumers. AI is a new tool. Like I mentioned, AI became a very small footprint, started with the 5G evolution, but it is going to be the fundamental tool or fundamental platform for the 6G communications. The way the protocol exchanges, the message exchanges that are going to happen in the current generations is going to change with the AI predictions. Cloudification of the networks. With the vRAN and kind of ORAN standardization, ORAN is a kind of standardization between the DU and RU, but vRAN is kind of give the flexibility for the operators to provide the RAN solutions onto their own cloud infrastructure in 5G. But it is not truly the cloudification as such. It is only certain set of the servers are going to be operated to host the RAN networks in the 5G. I think 6G in the timelines, it is going to become like a private cloud. All the cloudification of the complete networks happens. That gives more flexibility, elasticity for the service providers to operate and stretch the imaginations beyond these hardware boxes. And metaverse, like I explained, that XR is seen everywhere, and the quality of the XR vision is going to explode a lot, and much more kind of applications, use cases will evolve using the XR ecosystems itself. So there will be metaverse societies, metaverse towns will get created, and then gaming is going to change the young people's imaginations. So everywhere it can happen as a metaverse, and maybe sometimes maybe down the line in the future, all these meetings also can happen in the metaverse. And I will be sitting in the Bangalore and then presenting it. My real life hologram will come here and then present this particular keynote. It can happen. Yesterday, Dr. Magnus showed how the personal touch can happen between the friends, right? So, but to have that high fidelity metaverse related things, we need to have a lot of throughputs requirements, and there is a lot of latencies are involved. So, and of course, the last but not least, by looking at the device and digitalizations and ecosystem is getting enhanced a lot, there is a strong need about the sustainability goals and clean network technologies actually. So this is related to the energy savings. I'll talk about that. So based on these particular technology trends, Samsung has come up with what kind of requirements for the 6G. So there are 3 groups of the requirements we came up with the 6G rather than other previous generations. 6G requirements from the performance point of view, we expect that the peak throughputs going into the terabits per second. And normal user throughputs may come up to the gigabits per second. And latency is 1/10 of the 5G, that means almost 100 microseconds is going to be the requirement for the 6G technologies. Very, very hard, but let's see. Second group of the requirements that we came up with the architectural requirements. I think the current architectures are not enough to yield this kind of performance requirement that I talked about it. So in case of 4G, if you see that the cloud computing is happening either at the internet or at the core levels. Whereas with the edge computing came up in 5G, and RANs are getting virtualized, ORAN is got really everybody going through the ORAN related deployments. There is a possibility that we can create the edge cloud so that some of the services can be operated at the edge cloud so that the cloud computing can happen at the edge itself, at the RAN level itself, so that the latencies will come down with the 5G. That's the key low latency requirement of the 5G. But when it comes to the 6G, I believe that this kind of computing can be shared across the various network elements as well as the device elements as well. So we did this certain research related to the split computing of the AI/ML model, where it requires a lot of heavy computing running on the entire model, running on the one particular device, where the results and other things will get fetched in another device, in the device ecosystem itself. So that's where the sharing of the resources, sharing of the system resources can happen across the device ecosystem as well as the networks, whichever is nearby, whichever is having the less time to compute and then provide the real-time results, actually. So we are also researching related to that. It's not just the AI model, further breakdown into the several layers. Some independent layers can be layers of the network, AI/ML model network, can execute in one particular device, and another model can work in another device, and finally another device will, altogether new device will get the results. This kind of very architectural changes will happen with the 6G itself. By looking at the cloudifications and the data is getting shared across these particular device ecosystems, and not only the device ecosystem, but also into the network elements, the trustworthiness, security, and privacy is going to be very, very important. So we have to define the trustworthiness and then security architecture, and what kind of compliance need to be ensured to protect the device privacy, consumers' privacy, actually, consumers' data and then privacy. So this is another set of the requirements also will get evolved. So from the 6G perspective, the performance requirements, architectural requirements, and security-related requirements. So these are the three major important things which will define the 6G for the future. Now coming to the 6G technologies. So we believe that these are the key enablers for the 6G technologies to realize. There are many technologies are getting researched at this moment. I firmly grouped into the 6 different groups of these particular technologies. First, of course, the spectrum, right? So the people are talking about the high bands and terahertz related communications. With the terahertz, what kind of challenges are there? How the challenges can be resolved? These are the various topics, the spectrum-related discussions are going to happen. This is quite natural and quite natural technologies to be debated. Second is radio technology itself, right? So AI/ML and native platforms are going to evolve and then make sure that the radio technologies are going to be changed. And RIS is the basis, the reconfigurable intelligent surfaces are going to be the means for the millimeter wave as well as the terahertz going forward. And third one is about the network architecture that I talked about it, right? So there are many such kind of split computing related architectures need to be evolved, need to be defined in such a way that in what basis that the split computing can happen. And the security related architecture, security related trustworthiness, and to protect the data and privacy has to happen using the quantum safety mechanisms. And AI native systems AI native also will come into the air interface itself. So it's not just the CSI or the beam related techniques, it's about the radio predictions can happen in the AI native platforms at the wireless, at the core physical layer itself. And other aspects related to the green and energy. I think what is going to happen from the energy point of view, I think there are several questions in the last few presentations, is that can we predict the traffic of the networks and reasonably estimate that what kind of system resources or radio resources are needed and turn off the remaining things. For example, in the night, 2 a.m., if there is not much of traffic, it's not necessary to run the entire network with the full capacity. By having good prediction algorithms, we can turn off some of the radio resources so that we can save the energy, and then that will lead to the energy saving for the green networks point of view. This is the starting point. But there are multiple points will come up with the distributed network architectures. We can really make this green network methods. That's the research is going on at the moment. So coming to the terahertz communications, I will talk about the terahertz communication, little more zoom into this one, because this is the hot topic at the moment in Samsung, and we are also doing a lot of proof of concepts related to the terahertz communications. So naturally, high bands will provide a lot of high precision positioning and then the sensing capabilities. But it also provides a lot of technical challenges related to the path loss, and the current silicons are not designed enough to handle these particular high frequency ranges. And especially the power amplifiers, non-linearity will immediately kick in, and then it becomes obsolete, and then power amplifiers will reach to the saturations. ADC and DAC will consume a lot more power than it is happening in the low bands and mid bands. So these are the various challenges, and we did a lot of research, and then we made the certain POC. So this video is talking about the indoor test with 135 gigahertz as the carrier with 2 gigahertz bandwidth. We are able to make the 12 Gbps. We are able to see the 12 Gbps at the RF level with the 30 meters range. So this is this TX and RX. By changing the antennas also, we are able to meet this 12 Gbps requirements. When you take this same setup into the outdoors, so with this path loss and all these fadings and all these things came in, and then the throughput is dropped down to 2.3 Gbps, even though we maintain the line of sight, but of course the range is increased to 120 meters. So there is a lot of work to do on this particular topics. So there is a lot more challenges are there. We can see how to utilize this, how to research and then make the tech available for the subsequent years. I just talk about the spectrum because we are talking about terahertz communications, and if you see the spectrum, this is the snapshot of the Korea frequency allocations. It is so congested in all these particular bands. I think if you draw the same picture for the global as well as India, it's going to be similar actually. So how do we handle for the new generations or new technologies to evolve? So that's where we think that the new 6G range will be sub-terahertz bands. We think that 92 to around 130 or around 300 gigahertz, that is the range where the terahertz can work on in those areas. But at the same time, 6G is going to happen with the low bands and then mid bands also. So the strategy has to be in three folds. One should be that how to acquire the new frequency bands, and in the second case is that how to reform the frequencies so that it can be used not only for the 3G, 4G generations, it will be reformed to the 6G actually. And third one is the how to clean certain unused spectrums and then reshape it to the 6G. So these are the three major works that has to happen with the close collaboration with the WRC. All the technical work and POCs has to be shared with the WRC, and then make sure that WRC by 27, maybe 2027, they define the 6G spectrums. So these are some of the agreed timelines with the ITOR. So ITOR will finalize the vision by June 2023 for the 6G. I think by IMD 2030, by 2030, of course, 2030 vision also will evolve. 3GPP, in our opinion, this is our proposal to the 3GPP timelines, where the 3GPP should start working on the release 20 onwards, release 19 onwards to start with, but the 20, 21, 22 is going to be the major key milestones to standardize the 6G technologies. So in order to achieve by 2030, I think these are the timelines in our opinion. So let me talk about what the 6G from the global perspective. So this we have seen yesterday from the Dr. Magnus' presentation as well. There are many 6G initiatives, research initiatives are started. The first is started with the Oulu University, and subsequently many people has taken up and then created the 6G related research projects across the globe. From India perspective, the TSDSI is doing the very good job and created the task force. And I think there are various means of task force groups has been formed, and each of these task force groups will work towards creating the 6G proposals so that it will align with the 3GPP standardization. I think the timing is very, very right. TSDSI took that particular decision to create this particular task force. And Samsung is fully committed and participating in the two of this one. And Samsung, our standardization leader, Suresh, is TSDSI vice chair. So he's helping this TSDSI to ensure that all the proposals coming from the India is also get standardized in the 3GPP. From Korea perspective, Korean government is very, very aggressive to bring the pre-6G demo by 2026. They are requesting it, 2026. But we are discussing with them. But from the R&D core technologies point of view, they already invested about 200 billion Korean won, that is around $200 million. From the core technology, R&D core technology development point of view. In addition to that, almost $1 billion they are investing into the next generation network architecture, network R&D related technologies. So there are many projects are going on in Korea related to the 6G technologies, and we can see all these things are going to be realized. From Samsung perspective and Samsung commitment point of view, we released the 6G white paper in 2020. It is available at that particular link. You can download and then see it. I think most of you might have downloaded already. And recently, in this year, we released our spectrum timelines also, our spectrum proposals also, which will be released for the 6G. In 2022, we have made this white paper. So these are the two white papers. We released it, and we made the public demonstrations of the terahertz communications. So friends, that make my I conclude my presentation. So we as an ecosystem, industry, academia, and many researchers and all of us need to work together to build hyper-connected world for the future. Thank you.
Thank you, Dr. Mohan, and it was really a great pleasure hearing the vision and the goals for the 6G which you have mapped out. However, for us, the roadmap of 3 years, initial 3 years is very important because this is applied versus the research. So from that perspective, in the networking specifically, I'm interested in finding out what is your opinion on the satellite integration with the existing 5G network.
So, good question. May I know your name?
My name is Prakash. I am
Prakash.
from Emerging Open Technology Foundation, IIT Bombay representative.
Yeah. So, good question, but let me explain about from the satellite communications perspective. NTN, non-terrestrial networks, is going to be a very important research area that is going to evolve from the next 2 to 3 years, to be frank. So this means that there will be a base stations in the LEO satellites, or the moving drones will carry the satellites. So far that the base stations are fixed in nature. So when it comes to the base stations are moving, there is a Doppler we have to accommodate and then make sure that signal fading characteristics are will change. So there is a research is going on this particular perspective, and yeah, if it is satellite communications, the coverage will be very, very huge. So that's where that low bands and mid bands will help in that nature. Yeah, but we need to take care of the Dopplers and all these things. Yeah.
Thank you, Mohan sir. That's a great talk. One question is, as the Gs are progressing, we see the cell sizes are reducing because of frequency increase. Now we're hitting the limit of Wi-Fi. I mean, where Wi-Fi is this 100 meters or 60 meters is where Wi-Fi is very dominant.
Yeah, they are also going in that
They are
direction.
increasing their cell sizes,
Their
are
cell sizes
increasing, our
also
cell sizes are
decreasing.
So where do you think that we'll draw the boundary?
So I don't think the yesterday also this kind of question came up, that how Wi-Fi and how this cellular communications will go on. See, when the cellular communication, we are not saying that the terahertz communication is the only way for the 6G to realize, right? So it is going to be upper mid band and low bands. The band physics will not going to change, right? So that will derive the coverage areas. But how these utilize this based on the use cases, how these cells are getting utilized in what manner is going to change in the 6G actually. 6G or 5G evaluation itself, right? So we were talking, for example, in case of millimeter wave, it's my personal view, millimeter wave did not take off fully in 5G. Why? Because of this same, cell sizes are getting very narrower, and then the operators need to spend a lot of money to cover the areas. I think the people need to think about the fixed wireless access. I think there is a mean to achieve utilizing the millimeter wave. That is the reason when we started, Samsung started to realize the millimeter wave, the trials that we did with the fixed wireless access by providing the CPEs. So the convergence of the Wi-Fi, that where the cell sizes are increasing it, and then the backhaul of the utilizing these high bands with the 5G or 6G cellular things will be the future, in my opinion.
So instead of terahertz, why don't we move closer towards sub-infrared, because the path loss, as we get closer and closer to light frequencies, will keep reducing. So wouldn't it be a better option to move closer to sub-infrared than to stick somewhere around 300 meters?
So basically that particular spectrum is available at the moment, so that if we can solve that path loss related challenges, then we can have the performance requirements of the gigabits per second actually, or terabits per second, that the peak throughputs that perform 6G requirement is being set up. So that's the obvious choice for the people to go and then utilize this particular spectrum and then do the research and come up with meet these performance requirements.
So I want to understand from you, Dr. Mohan, that you have millimeter wave, you have the standard, whatever we have, sub-6. Now, carrier aggregation can extend. Like you can have a bearer at the lower level and have the, that is guaranteed at lower, and then you can expand as the application requires to the higher bit. Can this not be extended even to the terabits, carrier aggregation, so that we can apply what we learned from this into that? Is it a possibility? Is there anything research going on this?
So it's too early to comment about the carrier aggregation to how it will be co-work between the millimeter wave as well as the terahertz. Because the terahertz itself will pose a lot of challenges at the radio level, right? So if you have power related stuff, and we have the uplink power limitations from the device perspective also, right? So once it is being realized from the deployment point of view, probably either ENDC like the 5G has taken up and provided the NSA deployments, and then slowly they are also migrating into the SA deployments. May happen, but from the deployment strategy can be different, like you mentioned, from the carrier aggregations and the EN-DC kind of dual connectivity or triple connectivity probably.
Okay, thank you.
All right then, let us thank Mr. Rao for that excellent presentation.
Thank you, sir. I would now request Professor Lal to kindly felicitate Mr. Mohan Rao with a small memento as a token of appreciation.
Thank you.
Our first session of the day is on AI/ML for 5G advanced and 6G wireless systems. I now invite Professor Kiran Kuchi to moderate this session. Professor Kiran Kuchi is a professor in the Department of Electrical Engineering at the Indian Institute of Technology, Hyderabad. He leads 5G advanced and 6G research and standards development efforts at 3GPP. Professor Kuchi is the author of more than 200 international patents. Some of them are declared as 5G standards essential patents to TSDSI and 3GPP. Professor Kuchi founded Visec Networks Private Limited at IIT Hyderabad Technology Incubator. IIT Hyderabad and Visec jointly developed and commercialized 5G base station and user equipments IPs and narrowband IoT SoC. Professor Kuchi, floor is yours.
Good morning. We have several talks on new and emerging technology, the use of artificial intelligence and machine learning in future wireless systems. We have diverse talks. One talk on AI/ML techniques for the wireless network, more into the deeper parts of wireless, and the rest more of an application type work. So I'm glad that we received these proposals and presentations for here. This is really a new area. Machine learning has found profound applications in other areas, more traditional areas of signal processing like speech and video, and so many other fields it has found its way. But let's hear from the speakers about this new work they're carrying out. The first talk is by Mr. Kumar, shaping the future of air travelers' experience using AR, AI, and the future communications. Kumar is an alumnus of IIT Madras and IIM Calcutta. He has extensive experience in companies like Deloitte, Cognizant, Tesco. He has built his own startups in analytics, e-commerce, and remittance space. He's been selected for 5G Hackathon, his proposal. He is working for Visal Limited. He's leading a team which is working on a POC for airports. So let's hear from Mr. Kumar. Yeah.
Thank you, sir. And thank you everyone for being here. Thank you for giving the opportunity to present this. So I represent this company called So the structure of this presentation is this. I'll introduce the company which I'm representing and then give you a brief business context on why actually we are doing what we are doing. And then I kind of have a small demo and then a video recording screen grab from a mobile phone. And then we'll take you through AR, AI, and why are we doing this stuff and what are we doing, and then conclude with a vision for 6G. And when 6G comes in, how the world, especially the airport experience, would change. So this is a company that I represent. It started off as Wipro Airports India Services Limited, Visal, and then it kind of grew up into a 400 employee company. And so you name it, walk into an airport, you see the kind of boards where you see where the flight is. You go to the baggage, all the CCTV cameras, and anything and everything which you see with technology, including the data center, the private data center, which is a regulatory requirement that every airport should have its own private data center. It's all managed and maintained by Visal. Just the company overview. And so this is the key factor on how we decided as a company that we should actually go into AR and AI. And this is a chart which is more, it's an industry chart where you will have various generations for airports, like airport 1.0, 2.0, 3.0, and 4.0. In airport 3.0 is what actually you would see everywhere. So if you go to an airport, you walk in, you will have the biometrics done, there'll be a security check. They will actually take your photograph, and then they will validate with your passport if you're going abroad. If it's in India, then they validate with your any of the authentication card, and then they will let you into inside the airport. And that's the airport 3.0. When airport 4.0 evolution started way back in 2015, when we said that all the devices and everything in airport should be connected, and that's where AI and virtual analytics and blockchain kind of solutions happen. And today, in August 15th, the government had launched this application called DigiYatra, which works in Hyderabad, Delhi, and Bangalore airports, which will be the first time ever any airport is having a blockchain-based wallet and an artificial image recognition kind of a solution, whereby all you need to do is you just download the app DigiYatra and kind of validate with your DigiLocker, take your boarding pass, and in 30 seconds you can cross any gate. You don't need to stand in the queues, and there are 2 gates in entry as well as in the security hold area. So we have seen, and Visal is instrumental in getting the things together. So as of now, as of today, as we stand and speak, we have blockchain being used in airports. We have AI being used in airport. The question is, was posed to me when I was taking over as an architect in emerging technologies, was how do we take this to the next level? How do we move this frontier? Or in industry, we call it move the needle, basically. So the top line should grow, bottom line should grow, but at the same time, the investment should also happen in the futuristic solution. And that's why what I learned way back in IIT in 2000 about e-commerce was booming helped me. Because when we are looking at emerging technologies and how it is used in the industry, one of the thumb rule is you should see whether it is actually happening around in your industry. And if it's happening and somebody is doing that problem in some way or the other, and that can be improved in the technology, only that will, resonate with the customer who's going to pay you, and it will resonate with the technology, because the market is ready, the technology is ready, and that's when you know that the time for technology has come. And timing and technology into the market is one of the very important factors in actual technology building and development. And that's where I was looking around. So what is the logical next step to take? So then we have AI, we have virtual assistants, and when you look around, you will see that. So we have all the data and everything in two-dimensional screens. You take it a mobile phone, you take it a TV, you take it anything and everything. It's all in two-dimensional rectangular screen. So every of your information, artificial intelligence is is held in a two-dimensional screen. But it is of great use if it actually is launched in front of you. At the time when you need it, if the insight is given to you, then you will be able to use it better. Say I know so then we look at how is it. So what is happening in airport scenario per se. Now we know that then the way to move up the needle of AI and virtual assistant is bringing AR into it, and AR being looked at more like a UX of a spatial world. So we are talking about a future where instead of a mobile screen, we are going to have a spatial world, maybe in a specs or kind of format, but we are talking about the spatial world. In spatial world, the UX of the spatial world is going to be AR, is the hypothesis. And now, in an airport scenario, what's happening? And all the airports you would see, so all these examples are from news clippings abroad, because I was not cleared to use any Indian airport context for security reasons. But you would see it happening in every airport you go. There is a robot, and robots do a wide variety of stuff to you, and then and they improve the passenger experience. That's the expectation from the robot. So then we looked at what is these robots actually doing. You would see food delivery. If you walk around the exhibition area, there's one company which is actually cleaning robot, and they are actually supplying to one of our airports. And so cleaning robots, food delivery robots, these are the real robots happening. But from a passenger perspective, what are the other things robot handles are twofold. One is giving the information on the passenger needs. You go to the robot there and you talk to it, say, it's my boarding gate, where is my boarding gate? It's my boarding pass, where is my boarding gate? The robot will tell you. And there are robots which will actually take you to that boarding gate. Like, can you take me? And then it's a small fee abroad. You can scan your boarding pass, and then the robot keeps walking. And can we have the video if it is? So then we said, okay, how do we actually bring these robots in reality? And this is the screen grab, so it doesn't have voice and all of that. So we open the camera, and the thing which below you see is the Google Map kind of a thing, which I kind of measured and drew it in PowerPoint, and then I put it there. And this is the augmented reality solution. And we have a point, so it's taking you to main entrance of my office, this office in Gurgaon. We are actually piloting it in airport, but I'm not supposed to bring the airport scenarios. We did the entire thing in the office. And as you see, as I am walking, you would see that below the SLAM or simultaneous location mapping and maps of the mobile phone is used. And this is a small toy which I played with, saying, if I put a cartoon kind of a character, how will the cartoon kind of a character will change, and can I follow the character? And then this is the third visualization. It just shows the path. The difference, and the differences between all these three is the first one will always be stationary. The second animation will kind of guide you wherever it takes you, and the third animation is about the Toon Fox. And when we see from that, so the first part, right, the answering questions, it's nothing but Siri and an assistant standing there. And these are two assistants which are exploring. One is that robot thing, because it's a robot. That's what I told the entire team we're going to build a robot. But then the Toon Fox was more exciting when I kind of showed it off to people, and then they're looking at, okay, this fox also could be tried. So it's more to be an avatar at this point in time, sitting there answering your questions over conversational AI. And I'm using vid.ai in the backend. That's because it's free, Facebook's commercial and stuff like that. And why? So the question is, this is what you kind of saw. But why should we need a high-end? It's working in the mobile phone, and well and good. Actually, you can take it and walk around and you can use it. But in an airport scenario, the challenge is terrorist threat. And whenever they want you can't take the maps out, because if a map is to scale, they can plan anything, and any exact bomb can be kept at that place, and then blast can happen. So we need to actually dynamically allocate the maps. So a passenger, because of security reasons, all the maps cannot be downloaded. So the compute, which right now we are doing with mobile phone, because it's POS, has to actually be moved to the edge server, which we are maintaining anyway. So the compute has to happen in the edge server, which is within 1 kilometer radius of the airports, and it has to be delivered, and it has to be done in a seamless way. The challenge is, say this application, normally if I are having leisure time and you just don't look around, you'll be looking around, not be looking at the mobile phone. This will be used only when in the last minute I have to run to my boarding gate, I don't know where is it, there are like about 50 gates, and I look at this app. If the communication is not seamless, and if it's going to buffer, I may even miss the plane. And the fault lies with the airport, because its application did not allow him to run. And also the advantage for the airport staff is, the moment you are logged into this application, they also know your location. Because the challenge is, if a passenger gives his luggage for boarding, and he doesn't board the flight. If he doesn't board the flight, then he has to, the baggage has to be taken off because of security concerns. So then comes this point. So wherever he is, it has to be seamlessly communicating, and the location also has to be communicated. So we need a photograph of the location has to be taken, and in the back end it's the CNN thing with every 101, you kind of have that. Hundreds of photographs done, train neural networks to instantly say this is the location, and from here this is how you are going, and everything has to be seamless. And this is what we are experimenting with, trying to see if holoportation is possible. And this is one of the reasons why this 6G use case is important. And this time you're doing it with an open source called ARJS and A-Frame, where video call is possible, and we need to do TensorFlow and kind of a cut, which doesn't happen right now. Then you can actually have a holographic call in reality. And And when it comes to 6G, this is the vision map which we actually charted out. And this is based on a Harvard paper wherein you say, you need to have a purpose, core values, envision future. And then that's how you have developed the vision. Our vision is essentially to ensure that passengers should seamlessly travel from the main gate to the airport, which you don't see when you go. You see a lot of queues today. But with technology, we believe that queues can be decreased, and people can actually seamlessly go ahead. And also airport staff with holographic technology need not actually stand there. Instead of a biometric, instead of a CCTV camera, there can actually be a IoT person standing there, not only actually monitoring for threats, but also helping the passengers navigate. And way forward is, passenger experience to smart security and moving on to operational efficiency to ensure that Indian airports are safe and secure. At the same time, passenger gets the best experience possible. Thank you. Questions? Questions?
Thank you very much for the excellent presentation. One question relates to non-infotainment or not related to this, but as an airport authority, do you manage or do you control anything, the air flights, etc., with your...
So our company doesn't do it. It's just airports, actually.
It's only airport.
Only airports,
okay.
correct.
Thank you.
Thank you. Yeah. Thank you so much.
Thank you, Mr. Kumar. We will take the next talk. Subramanya Prasad Narla, Institute of Science, Bangalore. Ray integration with NS3 on HPC system for reinforcement learning for telecom network management. Dr. Narla is a consultant working on real-time optimization for 5G at Robert Bosch's Center for Cyber Physical Systems at the Indian Institute of Science, Bangalore. He also was a project engineer at SLK Bangalore. He has experience in natural language processing and computer vision. He got an MSc degree from Indian Institute of Science in aerospace engineering. He also got a PhD degree in mechanical engineering. He has a good mix of different backgrounds. He also taught at MIT Bangalore. I will be very glad to hear from him on this new and interesting topic. Thank you. Please. Yeah. That's okay, yeah. So he has a recorded lecture today, so he couldn't make it. Let's hear recorded message from him. Thank you.
Good morning everyone, I am Subramanya Prasad Narla. First of all, I would like to thank the organizing committee for giving this opportunity to present our work in this conference. Now I am going to discuss about integration of Ray with NS3 for reinforcement learning, which is used for managing telecom network. It is known that 5G networks are deployed in conjunction with existing 4G, 3G and 2G networks, which creates a heterogeneous network environment. However, existing RAN functions such as admission control, MAC scheduler and mobility management are still static rule based, in the sense that they are not dynamically reprogrammable to the requirements of new services. To this end, adding an intelligent layer to RAN functions can lead to more efficient network resource utilization. Focus of present talk is on real-time optimization framework, which is needed for managing complex 5G networks. This is the proposed architecture for real-time optimization framework for 5G networks. It has an AI-based real-time management framework, which has two components. One is the decision support engine and other is model learning. This AI-based framework uses AI or ML models to optimize the desired network performance metrics. Based on the learned parameters, decision engine returns actions to drive the real network. However, in our case, we don't have access to real network, so we used NS3 simulator coupled with a mobility simulator. And this NS3 simulator is connected to the AI framework through SDN controller, so that once the training is done, the AI framework can disconnect and directly you can deploy on a real network. Here we can also see we created a digital twin of NS3 network, which I am going to discuss in the coming slides. Network management functions involves sequential decision making, and it is well known that reinforcement learning is a potential candidate for learning optimal decisions. RL uses a reward signals to learn optimal policy. However, training an RL algorithm is a time consuming process. To this end, to speed up the learning process, we use Ray framework. Ray can be deployed on a HPC cluster, and you can run distributed Python computing tasks on them. Ray supports two modules. One is Ray Air and other is Ray Core. Ray Air is a high-level API libraries. It has a data library which is used for data processing. Train is used to train the AI models, and tune is for tuning hyperparameters. Serve is used to deploy applications, and RLlib is used for training reinforcement learning algorithms. Apart from this, Ray Core enables scalable apps which are written purely in Python using tasks, acts, and actors and objects. RayRlib is used for distributed reinforcement learning. RayRlib also supports deep learning frameworks such as the TensorFlow and PyTorch. Here we can see the implementation of DQN architecture. It has a set of rollout workers. Each rollout worker collects experience sample, which is basically state, action, reward and next state. This tuple is collected from each rollout worker and they are concatenated to form sample batches. And these sample batches are pushed to replay buffer, and learner extract a fixed number of samples from replay buffer, and these samples are used for training deep neural network. The updated weights of this learner network are again broadcasted back to rollout workers, so that the networks in both rollout worker and learner are in sync with each other. This is the proposed architecture for large scale RL based network simulation. Here we have an S3 simulator which is connected to OpenAI GIM through NS3 GIM interface. NS3 GIM interface is used for solving RL problems in networking area. The communication between GIM and NS3 is using ZMQ sockets, which uses protocol buffer library. In order to speed up the learning process, we use RayRLlib. Here, NS3 simulator provides the environment, and OpenAI GIM is used for implementing algorithms like DQN and PPO. We have proposed the proposed framework is tested with a simple handover example problem. Here we created an LTE network with 2 base stations and 1 UE, and UE is moving along the line AB with constant velocity. It takes around 75 seconds to reach point B. Here we compared RL based handover algorithm against the static rule based A3 handover algorithm. As you can see from this figure, the dotted line is the ideal handover triggering instant, after which the serving based RSRP is continuously decreasing, and A3 handover happened at around 50 seconds, whereas RL based handover happened at 40 seconds. This clearly indicates that RL based algorithm is performing better than static rule based A3 handover. Finally, I am going to discuss about the creation of a digital twin by parallelizing NS3. The main motivation for parallelizing NS3 is to enable faster than real-time simulation. Here the core idea is to divide LTE network based on UE. So here in process 0 we have an LTE network with U number of UEs and E number of E-node Bs. This is the NS3 simulation. And we created process 1, process 2, process 3, such that in each process we put only one UE, and the position of E-node Bs is replicated across all processors, and these processes are connected to GIM framework, on top of which we have RLlib. Here the main problem here is that whenever for example a handover happened, that like from base station A to base station B, one should also update this information in all the processors. This is one of the main problems that we are facing in creation of this digital twin. We could not update the E-node B informations in all the process. Basically, NS3 simulator provides P2P links for parallelization. If you want, let's say if you want to fragment a network, we have to use point-to-point links, and we have to break the network at the point-to-point links only, and we can keep the fragments in each in separate process. This is how the parallelization is done in NSD. However, parallelizing wireless network is extremely difficult, which is the main problem that we are facing. There is a need for rewriting large scale code. However, if you have access to rail network, as I shown in the first figure, you can directly deploy the AI based framework on a rail network, so that you can learn from the rail network and also you can test it on rail network. So the present work is done in collaboration with CDOT and CDAC. We would like to thank all the members of MPP Lab project for their constant support. This work is funded by MIT. These are the references. Finally, thank you to all of you.
So you know that this is a recorded talk. If you have any question, please communicate to TSDSI, and we can get you the questions answered offline. Thank you. So we'll move on to the third talk. Connected intelligence for data-driven fleet management. I invite Mr. Prakash, who did his MTech IIT Bombay, 80 batch, 78 BE from MSU Baroda. He is co-founder of eMerging Open Tech Foundation India. He is the co-chair of IEEE International Next Generation Roadmap, Edge Service Working Group under IEEE Future Networks. He has 40 years of experience, more than 40 years, and he is an entrepreneur, prolific speaker on 5G, cloud, edge computing, AI, ML, promoter of open source and open technology globally. We're very happy to have you, sir. The floor is yours. Thank you.
Thank you, Kiran Kuche and Dr. Kiran Kuche and TSDSI and IMC 2022. I am greatly honored to be able to present my viewpoints. So I will start with a little bit more on what motivates me to come here. I am part of Emerging Open Tech Foundation. I am also a member of CCICI and various other IIT Bombay alumni association. My focus is 30 years back, I'm an old generation guy. 30 years back, we did a mistake of focusing mainly on the service rather than the product. And there were companies they tried, but however, the requirement at that time for investment was high. So the motivation here, why I am pushing myself to bring here is make in India, for India, by Indians. So if I ask a outsider, India, saying that, why don't you come here and do work for us, we'll pay you. Very few people will take it. Whereas on the contrary, you say our people that we'll pay you and we'll go and work for them. So unfortunately, that has to change. And that's the reason I am motivated to be here. Okay. Given that background, I will move on to the presentation. So how do I forward this? Do I point there? How does it go? Can you explain me? Okay, I'll do it. Okay. So, to do justice to the topic, first, There are three elements to my topic. One is connected intelligence. When you connect, you can apply intelligence. Second is data collection. Because if you want to apply intelligence, you need to collect data, and then you have to model them, like previous speaker had mentioned about reinforced learning based on the convolution neural networks, which is what nothing but bunch of weights added to multiply add, and then you provide some kind of a model. So that's the second one. And the third one obviously is the fleet management. So connected intelligence, data collection, modeling, and the last piece is fleet management. So these are the only three topics I want to cover because this is a short period, and what I can do justice is only that. However, I'll go around, I'm bound to go around a bit here and there, but try to, within that, I'll try to explain. Why is it that? Okay. This is a big picture, and I think most of it is covered in this, okay? So first thing is mean sea level. That's the ground floor. Up to 1 kilometer, you do terrestrial networking. That is, you do all your cell phone, your Wi-Fi, anything that can be within 1 kilometer above mean sea level. Within that, you try to do all this. So that is terrestrial networking. And there you can include marines, you can include bus traffic, you can use all those things. Second, above 1 up to 10 kilometers, you have called low altitude platform, LAP. And in the low altitude platform, you generally tend to use the drones and maybe some UAVs, but better UAVs are in the HAP range, but that is high altitude platform. I'll come to that. So low altitude platform is where you generally try to do drones and try to do some of these UAVs at the lower end so that you can do reconnaissance, whether it's for the military purpose or for civil purpose, you can use either of them. Then from 10 to 17, generally that is reserved for the air flights. So your air traveling, whatever you do, that is the commercial space. So usually you don't get into that area. That is meant for air traffic. 17 onwards up to 30, usually you try to do the high altitude platform. The high altitude platform requires, like example, we want to do some missiles, and they call it as hail, mail and all that. That is high altitude, long enabled, so that you can run over 10 hours, 20 hours, 24 hours, because reconnaissance takes. So you've got missiles and all that. So that is a military application. And there can be other application like taxis, air taxis. Air taxis can go in that range where it can be deployed based on like Boeing or Airbus or Indian aeronautical ADS. They can provide some kind of a vehicle which can be transporting very fast so that you don't have to deal with the land travel. Okay, that's one application, and that is very important. And then I will go top down now, because anything above 30 kilometers up to 160 is called virtual LEO. So LEO is low Earth orbital. So I'll go top down there because you have got GEO, which is the GEO global, and then you have got medium Earth orbit. So global Earth orbit, medium, and then low Earth orbit. So they are somewhere ranging between, let's say LEO is up to 2000 to 2500 up to probably, and some figures which are exacts are there, but MEO is where GEO is focusing, LEO is where Bharti Airtel is focusing. Each one has their own territory. Why they do it, they have reasons. And GEO is generally the standard at the level. So we talked yesterday, one person asked why did we not speak about Gagan and the Navik? Okay, I'll say Gagan is nothing but it's a augmented, they call it SBAS, that is you augment whatever is standard. And the standard is you have to triangulate the 3 or 4 and bring the more accuracy up to standard, which is 5 millimeter positioning you can accurately measure. But when you go beyond that, you want to have 1 meter and all, it is augmented. So NAVIC is nothing but augmentation services, especially to position. You can also do assisted GPS on your cell. So there are many methods, but I think Gagan is lost its charm. I believe it is time for Magan and Ligan, because you have to do at the medium Earth orbit and at the low Earth to get better accuracy. And Lagan, which I am mentioning, is for low Earth orbit. This is not existing, okay? I'm just throwing some ideas which you can leverage for research and all. So at the north and south pole, you just mask out, and then that is equatorial and tropical, Tropic of Cancer and Tropic of, this is what is covered by the LEO. And so in that respect, it's important to note that your electromagnetic waves, EMW, is very important. And just to, because this is the main I am focusing here, if you do perpendicular to Earth, that is your EX. If you do along with the surface, that is EY. So your electromagnetic wave is X and Y. So normally you do linear polarization for most of the thing, but in the case of satellite, you need to do circular polarization. So you take an anti-clockwise or clockwise. So you can think of a corkscrew-like thing. That is the way you do helical, and so that is important because it protects you from getting corruption because of the noise and atmospheric water and air droplets and also. So in the case of a UAV or something, you get icing, you have to de-ice. So that means your throughput and your payload gets ruined by that. So to remove that, you have to take care of. So it is better to do in the C-band with those kinds of a operation. So this is general about the satellite. So I think I should stop here. I should go into the next slide now. But if you need more, you can talk later. But let me focus now on the priority here. So connected intelligence. So when we talk about connected intelligence, I am talking of the connecting the vehicle. So you can have a vehicle in the ground. So motor, bus, whatever, tractor, those are at the ground level. Then if you go at the, what you call the topology, obviously it is peer-to-peer or mesh network, one of the two you can do. So if a vehicle talks to another vehicle, if it's a patent tank going and doing some work there, we need to make sure that they are platooning, they are coordinating. So you need some coordination, V2V. So that is called vehicle to vehicle. So you can have vehicle to infrastructure. Example, you have a pole and you have got something there, antenna, and then you have to connect with them and you are able to do that. So you can have V2V, V2X. Those are the general, and topology depends on how the nodes are distributed. You can have a DAG, or you can have distributed, that is, you can have edge and the node, and you can connect them with various topologies and optimize them. Pareto optimization, so you have multiple variables and you have to optimize that. So those are available. Now you can also connecting the fleets in the air. So I can have air-to-air communication, and it should not like MH15, like that Malaysian airline disappeared as a whole. We don't want that kind of a thing. So we need to ensure that we can have that kind, and plus avoid accidents and all that. So for safety purposes, those are used. So you can connect fleets, and you can collect the data on them. And once you collect, you can clean up. And like RL, reinforced learning, there is a GAN, which is like you fake the data and then create the sample, and then you, against adversarially, you put different than that. That is, whether it is real or fake, you will not know. How do you, so that distinction you can make, and that is GAN network. So GAN, RL, CNN, DNN, name it. The supervised, unsupervised, SVC. So you've got many modelings which you can use. But hypothesis is the most important thing. Once you have a hypothesis, you have to prove whether we can do it correctly or not, and then how do we remove the error, whether we need integer precision or whether we need a lower precision can do, because decision-making prediction is based on what the data collection is there, what is that you want to adopt it for, and how you want to adopt it for. So that is connected intelligence. I will stop here. of course, the fleet operation is important. So next is, we talk about vehicle, ground, air, space. So gas, ground, air, and space. Air is generally atmospheric. Ground is what we are talking about, the mean sea level, and the highest one is the space. So it's called three gas. Gas is ground, air, space. Now in these three, we want to do next generation networking. Next generation networking is what? 5G, 6G, combination thereof, adding AI intelligence, AI ML to it. So all this means we need to be able to project on the 3D. That means r theta phi, or it is XYZ, whatever coordinates you talk, altitude. So because this is electromagnetic waves and all that, so that is what is used by radio. You can use LIDAR also, that is light emitting LEDs, and LIDAR is ranging for using the light. You can use radar using the radio. So LIDAR, radar, these are all part of the object recognition mechanisms. So when a vehicle is driven, you have to identify the path, how it should go. So path determination is based on the ranging, whether it is light-based or radio-based. And then there are equipments available for that. So when I say 3G application, this may mean you can use a Wi-Fi. It is not that Wi-Fi is ruled out. You can use Wi-Fi, you can use cellular, you can use combination. It's all heterogeneous. At the terrestrial and non-terrestrial, you can have in between, like you have a base station here, I can put a base station on a space station. And then that will be a different characteristics. So extending the edge to the air and the space is the next wave, where we need to focus as a research to find out how we can apply this. Today what exists, but how can we apply this to edge, which is, edge is going to be the 75% of all the data coming and going. And that means what? We have to focus on the edge. So extending the edge beyond what is considered as edge in the ground in 1 kilometer should go to 36,000 kilometers up to. So extension of edge into air and space is one of the key, and vehicle on ground, air, and this is what they do in terms of, and yeah. So I will just be winding up quickly. So let me go. So beyond that, can I? Yeah. So connecting together, we can do P2V, P2 mesh. I have described about P2V and mesh. And so you can connect and then you can apply the intelligence. Collecting fleet data, as we saw in the previous case, we had a pipeline. So there is a pipeline architecture for data collection. You can use TensorFlow, you can use PyTorch, you can do a lot of combination. There are plenty of modeling and availability of resources to apply. And then at the end of that, you apply those and ensure that you go to better precision and better navigation of the vehicles. So the idea here is V2X, V2V should be applied for path determination and error. So that safety, there are 5 levels of safety, which is the major thing. I will say that level 0, 1, 2, 3, 4, 5. So what is applicable to the autonomous driving, like you brake, stop, or you want to do a steering in the highway, or you want to do a various kinds of maneuvering for the safety, or just drive it automatically. So those are applicable also to fleet at the air, and it is much easier there, hopefully because of the free space optics and communications which are done at a better rate. So that's the, so basically I want to say that these are the 5, 6 methods whereby you can do. So the same level can be applied. So we want that some people in research find out, can we apply whatever we do for autonomous company, can we do it for the future in the air and in the space. So I think, fleet operation and management. So there is operation and management, that is nothing but a kind of a automation. Once you do manually, you automate it and you simplify it, and that is the goal of the fleet management. At the ground level, like you have a bus, DTC buses are Delhi Transport Corporation has a bus, and if you want that fleet to be managed, that's a public safe service. So you can use automation, you can use the Kubernetes containerized, etc. And at this time, I think I should thank you all for listening to me. I may not be very focused, but if you need anything, we want that you should be able to come back to us, and we want you to do independently research and practical research, applied research in next 3 years to enable India to make in India for India. Thank you very much.
Thank you. We can take some questions.
Yeah.
Sir, I'm Chanchal Chakraborty. Just I want to ask one question.
Sure.
Are you finding any application of reconfigurable intelligent surface on the drones and others on the terrestrial communications so that you can have cell-less architecture for the future generations? What's your view, sir?
I'm pretty much convinced. That's the only way to go, because cost is important. And for Indians, cost is one of the first factors. So reconfigurable surfaces which are projected for the architecture for the 6G is definitely a welcome. And not only that, it can also be, that is what I said, the polarization. Circular polarization, if we try to use even in the devices, that will become really great. But that's not there yet. But the Vivaldi antenna along with the slotted patches and all, that's welcome. I think it is a good way to go about.
Yes, sir. We have found that the circular polarization metasurfaces are getting generated. Some research papers have found. I think that's a way of carrying on, right?
Correct. I believe I have seen the research papers, and I'm definitely confident that one of our students of this IIT Bombay, Delhi, Kanpur, all these people, they are experts. And CVIT, I should not forget CVIT, they are really great. And we want them to definitely work on that and do in a different way than what our past people like us we did.
Another question is that are you finding that on the space, I mean, there will be an applications for the inter-satellite communication.
Correct.
The application of the millimetric wave and terahertz communications, and how the RF challenges and the circuitry challenges you are finding, because the terahertz, the loss will be huge, and the proper window needs to be found out. What do you think, sir? How to produce the chipsets for that particular terahertz communication in the IMC?
So inter-satellite link standards are evolving, S1, S2, S3, under the INGR, IEEE Future Networks, which I am sharing for the edge. We have a satellite team which has generally brought the standards, and those standards are evolving, and definitely there is a bypass mechanism, that is you can have hierarchical. So you can have a balloon floating and have some equipment there which can do a reflection. So this is a bent tube, right? Bent pipe is the standard for satellite, which is at the layer, physical layer. So you can definitely optimize that and even have a hierarchical, so that even in the space, whatever is there, you are able to do the kind of development Samir is doing. I am pretty confident you will have support from all of us. Thank you.
Thank you. We can take other questions offline. We'll have the next talk presented by Sresht Tuli, Imperial College London. He will talk about digital twin and AI-based sustainable healthcare using 5G and IoT. Sresht is a PhD student at Imperial College London, UK. His research interests include use of simulations and digital twins to optimize resource and energy efficiency of computational infrastructure using AI ML techniques. Please go ahead. Thank you.
Thank you for the introduction. Good morning, everyone. My name is Sresht. I am a PhD student at the Quality of Research Lab at Imperial College London. And today I'll be sharing some of my thoughts on digital twins and AI-based sustainable healthcare for 5G, IoT, and beyond. So at the dawn of the Industrial Revolution, humans embarked on this agatha-ecological journey that has furnished us several luxuries that we are accustomed to today. And many of these are thanks to the advances in computational and networking technologies, specifically that have been as part of the fourth version of the Industrial Revolution that we commonly refer to as Industry 4.0. And the key aspects in which Industry 4.0 focuses on includes these ideas that we're familiar with, including big data processing, cloud computing, autonomous design, IoT, data management, and so on. And here we assume that every IoT device can be a sensor, can be an actuator, and possibly with some intelligence embedded inside. So considering that context, the future is not all golden, and we need to proceed with caution. With the advances that have been in the last decade or so as part of the Industry 4.0, we now have millions, if not billions, of IoT devices active at each point in time. And this is projected to grow in the next decade or so. So to speak that we are now in a deluge of data, and we have so much data to process that it is becoming very hard to scale the computational paradigms that we are familiar with today. Another interesting aspect is that workload, services, users, their demands have become even more unforgiving, specifically in the case of various IoT, 5G, smart city kind of environments. And this makes service level agreement deadlines very strict, very unforgiving, and we want to make sure that we have response times so that we do not violate such agreements. To do that, typically, these big companies or any service provider employ very computationally heavy servers. Now, these would be, say, very big servers that have several number of cores and so on. And in typical silicon-based architectures, this imposes a lot of energy overhead, energy consumption for these different models. And as we increase the energy overhead, their carbon footprint also increases, not just in the terms of economical load, but also in terms of the environmental impact, just because once we are revamping infrastructures, the legacy systems or the systems that we are replacing, they typically end up in a landfill, and that raises sustainability concerns. In terms of the carbon footprint, we have seen that the global average temperatures have risen by at least 1.2 degrees Celsius from pre-industrial times, and it is projected to grow even further in the decade or so. By 2030, we should reach around 2+ or 3+ degrees, and as we reach that, we might reach a point of no return. And that is, again, a point of concern. However, the future is not so grim, and cautious technological development could help us achieve our sustainability goals. And there are various technologies that have come across. We have heard in this presentations in the previous speakers. And 3 technologies that I'm very excited about in terms of the further research are virtualization, distributed computing, and digital twins. These technologies, I believe, would be at the frontier of allowing us or enabling us to tackle the sustainability challenges because of various control surfaces that they provide. First of all, virtualization, which is just our ability to execute tasks and workloads or services at a level of abstraction that is beyond or above what typically is provided by a bare metal hardware. Now, this allows us to run workload, services, tasks on an architecture agnostic manner. Second is this idea of distributed computing. We're all familiar. We can run workloads or services in different, distinct, multiple nodes. And there are various paradigms that this is divided into: edge computing, fog computing, cloud computing, where typically edge follows this data gravity principle such that the edge nodes or the compute nodes are placed at the close of the edge of the network or closer to the source of the data. Fog nodes are somewhere between cloud and edge, and cloud nodes are usually at a geographically distant location, possibly at a multi-hop distance from the source nodes. The third technology is this idea of digital twins, where we can create a simulated replica of a physical infrastructure such that we can run various what-if scenarios, what-if tests on these simulated environments very quickly, just because these could be discrete time control event simulators. So with this context, let me now go into some ideas on why we should focus on sustainable healthcare. There are various ways in which we can tackle sustainability, but we need to decide and prioritize which sectors to focus on first in order to maximize impact, in order to make sure that we are able to convince the buyers or customers that this is something that can actually create an impact. And healthcare as a sector is very exciting for me because, first of all, it is an evergreen sector. And second, it has second highest emission across all sectors, falling second to the generation of energy itself. Another thing is that there have been various prior works very recently in the last 5-6 years, at least at Imperial College, where we've seen that digital transformation of healthcare workloads, for example, automated diagnostics, operation management, logistics, and so on, can be easily transitioned from pen and paper, brick and mortar to digital simulated twins. And this allows us to run various what-if scenarios, scale our workloads to be able to bring down energy, operational costs of healthcare as a sector. And one use case that I'll go through as a running example is this idea of smart hospitals, where smart hospital is like a smart building, where we have several IoT devices. Now, these could be sensors like cameras, energy monitors, and so on. We also have actuators like thermostats, light switches, etc., like what we have here. And there may be several edge and fog computing based nodes that can process these workloads. These could be even, say, the handheld devices, mobile devices that we have, or maybe a server on-premise private cloud or a public cloud service using a pay-as-you-go service. And this allows us to create a platform or a framework that allows not just running these different workloads like automated diagnostic on these fog and edge devices, but this is even bootstrapped together via the 5G and 6G technologies that are coming today, possibly using some intelligence embedded within these computational devices. However, it is very critical for us to be able to manage efficiently these resources, just because we do not want these resources, edge devices, to take up all the energy themselves. We came from monolithic architectures to distributed architectures for this reason itself, and we do not want our resource management to be not intelligent. We want it to have some sort of intelligence embedded. So one line of work that my research group has been working on for the past decade or so is this idea of using neural networks as surrogate models. And neural networks, as we know, are within this realm of deep learning, where they can approximate any arbitrary given function to any level of precision given enough data. And once we use this to model any optimization surface, for example, quality of service metrics like energy consumption, response time, fraction of violation of service level agreements, then these surrogate models can be used to run various search strategies to optimize decisions, resource management decisions. And these search strategies could be either informed, maybe supervised, or uninformed using various gradient-free approaches, gradient-based approaches that we have shown here. But the overlying idea is that when we consider something like a smart hospital as a distributed computing network system, it allows us to run various resource management decisions, optimization using neural networks as surrogate models. However, we cannot stop there. The idea of using neural networks as surrogate models is enough for decision management. However, when we want to scale this for not just a single hospital, but maybe a chain of hospitals, it makes it very hard to scale these neural network models just because we have resource restrictions at these edge servers. So what we can do is that we can build various simulated replica, very motivated from the digital twin idea. We can build a simulated replica that we call coupled simulator or co-simulation in short. And this loop typically works in 5 stages. So one is that we monitor a system. We have a physical infrastructure, possibly a smart building. We monitor various quantified metrics or empirical metrics that we can gather. Now these could be, say, the CPU utilization of various edge servers, and create something called a state of the system. So this state characterizes that system at any given point in time. And once we have this state, we can forward this to a surrogate-based decision model that can create multiple sample decisions or candidate decisions that we want to choose from. Why do we want to create multiple such decisions? Because inherently such architectures, such frameworks are stochastic. These workloads could be dynamic, and we could have concept drifts at all times. So we want to check multiple such decisions using a co-simulated model. And what happens is that we can create this tight coupling between the physical infrastructure and our simulated digital twin, wherein any change in the physical environment is also reflected in real time in our simulated framework. So what happens is once we have this current state of the system, we can send it to the simulator, and we can emulate the effect of such sample decisions on the quality of service metrics like energy consumption, operational costs. And once we have these effects, or once we have these deltas of quality of service parameters, we can use this to create a feedback loop back to our surrogate-based decision model to either tune that neural network itself or to decide one of these candidate decisions, which is the optimal one. And once we have an optimal decision, that can be enacted into the system, and we can reach another system state, just like a discrete time control optimization. So this is how we can leverage digital twins for optimization using AI and machine learning. Now that we have some overview of simulation as well as neural network-based optimization, let me discuss one of the critical challenges that we face in sustainable healthcare. And this is the idea of deploying neural network-based workloads, especially computer vision workloads, on these distributed architectures. The thing is that in areas like healthcare, we want extremely accurate, extremely precise neural models that have possibly 99% or even more accuracy. And many of us may be familiar that once we need these kinds of unforgiving accuracy demands, we need very large-scale neural models, possibly with gigabytes or even terabytes of parameters. So these models that are required for healthcare have exorbitantly high resource requirements, and they impose very high costs if we want to completely revamp the infrastructure. And as I said before, this also raises some sustainability concerns when these legacy nodes get to a landfill, and that could lead to high carbon footprint. So what we want to do is we want to deploy or employ these large-scale neural networks, but within these legacy nodes that have or impose some sort of resource constraints that we might not face in a proof of concept kind of a minimum viable product. So we developed this first of its kind approach, which we call split place, for efficient deployment and management of large-scale deep neural models in mobile edge environments. Yeah, so let me give you some basic background on how split place works. For more details, I'll refer you to our paper, which is accepted in IEEE transactions on mobile computing. And the idea is pretty straightforward. Rather than using the monolithic neural network itself, what we can do is we can split these neural networks into multiple fragments. Now, there are multiple ways of doing this, but the two ways that we use are described here, which is layer-wise splitting and semantic splitting. So what layer-wise splitting does is that when we have multiple layers in a neural network, we chunk them together or group them together into different groups or fragments, and we share each of these different layer groups to a different mobile edge environment or mobile edge node. And once we want to infer a particular input through this neural network, we just send it sequentially to these different mobile edge nodes, and we generate the output. Another approach is semantic splitting, which semantically splits the output of these neural networks into different fragments. And consider an example of, say, classification into 100 classes. What we can do is we can generate these likelihood scores for 10 classes each using 10 different neural networks. And these can be split, again, parallelly and run in a parallel manner to reduce the response time. And as shown here, there is a trade-off between layer splitting and semantic splitting. Layer splitting has higher response time just because of sequential execution, but it also gives us higher accuracy because in semantic splitting, there is no parameter sharing across these neural models. So considering this trade-off, what we want to do is that given the service level agreement deadline of a particular, say, workload or a particular AI model, we want to identify or take these splitting decisions conditioned on whether this deadline is more or less than an estimate of the execution time of a layer split model. So what this does is that once we have an estimate, maybe using exponential averaging and so on, we want to identify what are the different probabilities conditioned on whether that service level agreement or SLA is greater than this estimate or not. So once we have these different probabilities, we can train, using data-driven fashion, we can train various models such as multi-amp banded decision model to find out whether to create a layer split or a semantic split given a workload and its service level agreement deadline. In the interest of time, I'll skip the experimental setup, but we have a very akin to a very similar smart hospital in London, we have created a simulated or an emulated environment where we have 50 Raspberry Pi kind of devices. We have mobile nodes that create these different requests, and we run various computer vision-like tasks on our platform. And the results speak for themselves. We compare against state-of-the-art baselines and show that we are not only able to reduce energy consumption, but also improve the accuracy, reduce average response time, reduce the fraction of service level agreement violation, and improve the overall reward of the system. And all of this comes at slightly higher cost in terms of scheduling overhead. So this requires, in the broker that creates these decisions or takes that decision, the resource management becomes slightly higher. But overall, this allows us to make deployment of large-scale deep neural models feasible within legacy infrastructures. And that gets me to this key takeaway, which is simulations are extremely powerful. It allows us to generate various what-if tests, external feedback, to train machine learning and AI-based models that can then be deployed on 5G platforms or edge platforms that are running on 5G to be able to improve not just quality of service metrics, but also bring down operational costs and scheduling overheads. That is all from my side. I'll now take questions. Thank you.
A quick question to you. Very good presentation on the health and use of AI/ML on the health. So my question to you is, can this, whatever you apply for health outcomes, can you use less transfer learning? Instead of having just to do every time the same simulation for same ailments, why can't you have a model defined already and just use at the edge only computation you do first time? And you can personalize it, but use transfer learning to reduce your cost further down.
Yeah, so the discussion that I have been doing in the past 15 minutes was all about inference. Training, again, that's a separate story. There are various ways of doing training, federated learning, transfer learning, and so on. And the fundamental aspect or issue in training is that data centralization is a challenge. So once we want to train these neural network models, how do you train in a centralized fashion, but also make inference distributed? So either we have some sort of a central repository that has some sort of trained models, and whenever we generate new data through sensors and actuators, we can generate these delta weights and send it across. So that allows not just differential privacy, but also training these edge models in a far more efficient manner. I hope that answers your question. Sure.
Is that you talked about two types of splitting, right? Where the accuracy is one case is a challenge, and second one is the response time is a challenge. Can there be a hybrid model or mixed kind of some work is going on so that you can have best out of this? Both the things will be better, both in terms of response time as well as the accuracy. What's your view?
Yeah, sure. So currently what we have as part of this paper is that once we have statically decided that there is a layer splitting strategy and a semantic splitting strategy, we can create a resource management decision model, assuming that we have some sort of Docker containers or virtual machines available with static neural networks. But typically in practice, this is not the case. This is very seldom the case that we have static models and not dynamic models. So what we can do is we can do some sort of neural architecture search, and that can be concurrently designed with resource management. So we not just decide whether there is layer splitting, how many layers to split, and so on, but can there also be semantic splitting within the layer splits or semantic splits within the layer splits, and so on. So once we have that, then that becomes a concurrent design between which neural model we should choose or combination thereof versus what kind of resource management we should perform using these neural models. So that is the main trade-off that we can leverage. Sure.
Thank you.
Thank you. Okay, so the main objective is that currently in the past 100, 200, or thousands of years, we have seen natural evolution. The objective that I've been trying to demonstrate is that from now on, natural evolution would not suffice. We need to co-evolve with digital models, so there has to be both artificial and natural evolution together. And to do that, the fundamental or key aspect is this idea of digital twins or co-simulation, which would allow us to leapfrog technologies to further solve further challenges. That is the main idea. Thank you.
Thank you very much.
So thank you, Professor. So I'll start with the presentation. So yeah, the talk that I'll be giving today is AML technique for 6G wireless networks. So this is the brief outline of the talk. So in the first section, I'll give a brief introduction about 6G and what are the various challenges of using AML in wireless setting. And in the next section, I'll talk about AML for physical layer and the current work that is being done in 3GPP regarding this. And the last section, I'll give a brief overview of distributed learning. So when we consider 6G, some of the driving applications are expected to be multisensory external reality application, autonomous driving, extreme URLLC, and massive sensors and IoT networks. So if we consider most of these applications, we realize that most of these applications require more bits, more spectrum, more reliability with an even lower latency. Also, most of these applications generate a lot of data which is distributed among the devices and which can be leveraged for a better performance. So artificial intelligence and machine learning can play a crucial role in help us leverage this data for a better wireless network. So coming to AML for wireless communication network, if we consider the current communication model, most of this model relies on heavy mathematical models which may not reflect the system accurately. And finding the optimal solution for most of the tasks can be computationally heavy and sometimes even infeasible. And actually some of these system can have some nonlinearities which can affect the performance and which cannot be captured completely by the model. So considering the challenges, AML can help us solve some of these challenges. So using AML, we can model systems that are not completely represented by a model. So all we need is what is the input that is to be given to the model and what is the expected model. And using that, we can design an AML model which can perform that particular task. And finding the solution using AML model, which can be much more simpler than the usual heuristic-based or brute force methods. And also, using AML model, we can effectively model a nonlinear system, and which can actually replace the existing communication models. So coming to the current work that is being done in 3GPP and for physical layer. So if we consider most of the applications of AML in physical layer, they can be classified into 4 different levels of integration. At the first level of integration, what we do is that we take AML and use it for some specialized function, which is not fully solved currently. So some of the examples of this level of integration is like using AML for channel prediction, for uplink, downlink, reciprocity in FDD, and some interference coordination and mitigation. And in the second level, what we do is like we update some of the existing discrete modules using AML. So let's take the demodulator for an example. We can replace the current map over the log map demodulator with an AML model, which can give us a better performance with a less complexity. And in the third level of integration, what we can do is we can have different AML models which jointly perform a single task. So one of the examples that I can give here is end-to-end learning for physical layer transmission, where we can replace the existing error correction module, the modulator, and the waveform mapper using an AML model. And at the fourth level of integration, what we can do is we can integrate the AML with existing model-based method, which can improve the performance of existing method, also help the complexity and training overhead of AML as well. So coming to the current work that is being done, in release 18 of 5G NR, 3GPP has initiated a study on AML for NR-AR interface. So in this study, the main objective is like exploring the benefit of using AML for better performance and reduced complexity. So the way that 3GPP is planning ahead is that by selecting a few selected use cases, they will evaluate the performance of AML models. They will develop a common framework for the AML models and assess the potential specification embed for the AML models. So regarding the use cases that have been selected for the study, there are mainly 3 use cases. The first one is using AML for CSI feedback enhancement. The second one is using AML for beam management, and last is positioning. And within each of the use cases, there are further sub-use cases. So in CSI feedback enhancement, there are 2 further sub-use cases. The first one is using AML for channel prediction. So here the objective is using AML for channel estimation, which can help reduce the, give us a better channel estimation accuracy, as well as reduce the pilot overhead as well. In the second sub-use case, we use AML for CSI feedback compression. So currently, if you see the amount of the feedback that the UE has to transmit back to the base station can be quite large, and we may need some compression mechanism for this. So AML can help creating a model which can help reduce the overhead from the UE to the base station. So in beam management, if you see, there are again two further sub-use cases. The first one is spatial domain beam prediction, which is using AML for predicting the best beam pair between a transmitter and a given receiver. The second sub-use case is using temporal domain beam prediction, which is like predicting the best beam over time. So if a mobile user is moving, how to track the best beam for the particular UE over time. And in positioning, there are again two further use cases. The first one is direct AML positioning, and the second one is AML assisted positioning. So I'll be going a bit deep into this AML spatial domain beam prediction using AML. So if we consider, ideally, if you want to find the best beam pair between a base station and transmitter, what we can do is like we get the RSRP, which is the reference signal received power measurement of all the beam pairs, and then select whichever beam that has the highest RSRP to be the best beam. So in this scenario, what the base station has to do is like it has to transmit using all the transmit beams, and the UE has to receive using all the possible receive beams. So the number of beams that has been transmitted is also quite large, and the amount of feedback that is going from the UE to the base station can also be quite large. So instead of doing this using all the possible beam pair, what we can do is like we can take measurement from a selected subset of beam pairs and then give that measurement to an AML model. And the AML model can use the subset beam measurements to predict what is the best beam among all the possible beams. So if we do that, we can reduce the actual transmit overload also. Since we are not transmitting all the beams, we are only transmitting few selected beams, and the feedback is also reduced since we are not reporting all the measurements back to the base station. Yeah, so we have done made some contribution to on this regard to the 3GPP. So in our simulation setup, we have used a base station which has like 64 transmit antennas and which is used for forming 16 transmit beams. Similarly, the UE is equipped with 16 antenna elements and which is used to form 8 receive beams. And in total, we have like a total of 128 beam pairs possible. So for our AML, we have considered 3 scenarios in which each scenario has a different subset size. The subset size is the actual measurement that is being used by the AML model. So if we see when the subset size is large, so for example, when the subset size is like 64 beam measurement from 64 beam pairs, the accuracy of the model is larger as compared to the size when we are using only measurement from 16 beam pairs. So since there's a trade-off actually. So if we want better accuracy, we have to use a measurement from larger number of beams. But if you want to reduce your overhead, we don't want to use that many beam measurement. I mean, we don't want to use a smaller subset size. So there is a trade-off that needs to be investigated further, and I think the study will be considered on this during the next few meetings. Yeah. So now I will give a brief overview of what is distributed learning and what are the various architectures and some of the challenges that is being faced in distributed learning. So if we consider the previous example that we saw, each UE has their own data, which is being then fed back to the server, which is at the base station. And at the base station, we have an AML model, which collects all the measurement from all the UEs and use it for training and inference purposes. So this is like a centralized learning example where the AML model is residing at a central server, and all the UEs are reporting their measurement back to the server, and it is then used for training and inference purposes. So rather than having a centralized learning setup, we can have something known as distributed learning purpose, where the actual data is not completely transferred to the server. It can transmit an actual local model or some partial output to the server, and the server can collect all these local model and the partial output to build an aggregate model and then feedback it back to the all the local users. So the advantage of using this distributed learning is that we are not sharing the private or proprietary information with the centralized server, rather than sharing this local or private data. We are only sharing some partial of model details with the server. So some kind of privacy things we can have with this distributed learning setup. So as I said, in most of the wireless network, the data is generated and distributed among most of the devices. So if the user wants to keep their data private, we want something like we don't want to transmit that all the data that is being generated at the user back to a centralized server. So if we want this kind of setup, distributed learning can help us, in which we are not sharing the private data, we are only sharing some process data to the server, and we can build a unified learning algorithm using this process data so that you can perform a joint task among all the participating devices. So the main advantage of using distributed learning is that we can improve the data privacy of the users, since we are not sharing the raw or proprietary data with the users. So coming to one of the architecture used, one of the most common architecture is known as the federated learning architecture, wherein which each user have their own local data, which they use to train a local model. And once each user has trained their own local model, this local model is shared with a global server, which collects all the local models from all the users and then uses them to build an aggregate model. And once we have an aggregated model, that is then fed back to the local users, which can then use, which uses the global model to update their local models, so that you can, after this, when we perform this step a couple of times, and finally we will have a common model among all the possible users. So if we consider the beam management case that I talked about earlier, so let's say along with the beam measurement, you want to use a user location also for the beam prediction. And the user does not want to share their location with the base station or the centralized server. So in this case, you can use a federated learning algorithm, which will use the beam measurement and the user location to train the local model, and then they share the local model with the centralized server. And you can then aggregate this model and to build a global model, which will be shared among all the users. So one of the disadvantages is that the local model convergence of this local model into a common model are called so then I'll just skip this. So the next architecture is something known as split learning, and in split learning, instead of having one local model, what we have, one model which is split into multiple layers, some at the base station side and some at the local side. So you can use this split architecture to get some, instead of sharing this, let's say the private or the raw data, we'll be sharing only some process data. And these are some of the challenges that is there in distributed learning. So it's like some security convergence and how it will work in a wireless setting. So I think that's about it. I will conclude my talk. Thank you.
Just you have put down all the learning processes. Convergence is one.
Yeah, exactly.
Can you tell about convergence and accuracy information?
Yeah. So convergence, main problem is that in distributed learning, so how they actually converge and what are the resources and computing resources that you need. So how many local users that can participate in the algorithm. So there is a trade-off between all these. So that needs to be further investigated, and how they work in a wireless setting. So in wireless setting, there is the communication between the users and the central node is also not as reliable as to be, not as reliable. So how the convergence will work in a wireless setting. So that is like some of the challenges that needs to be solved.
Please.
So I'm having two quick questions. One will be that whenever you are having 64 beams, right? So some of the beams will be utilized for the vertical polarization, some will be for the
Yes.
Can you make a diagonal stack just like that, so that you can dynamically allocate these things based on the clutter, based on the time of call and all such things? So can you do it? Second, my question would be, with the advent of the quantum computing, how you are going to take the quantum ML for that? How you are going to address those stacks, AI ML stacks in the radio level itself?
So about how to select the beams, I think that is also, there are models which can do that. So based on how the users are distributed among the cell, you can have a model which can predict which is the ideal beam and all that I mean, what is the best beam, how many beams you have to transmit in one particular direction, what are the beam width to be used. So there are models. So regarding your second question, I'm not that familiar with this quantum AML.
Okay, thank you. We'll move on to the next talk. This is by Mir Ahmad, IIT Delhi. Necessity of Edge AI ML in teleoperation of robots. Munib is currently a PhD scholar at IIT Delhi. He received his master's degree from Jamia Millia Islamia University, New Delhi. He is interested in Edge AI, haptics, computer vision, ML for robotics, and artificial intelligence involving images and signals. Please, yeah, thank you. Yeah, just go ahead.
Good afternoon, everyone. Thank you for the introduction and letting me speak here today in front of you. So today I'm going to be talking about necessity of Edge AML in teleoperation of robots. I am with IIT Delhi in a team led by Professor Lal. So the first thing that I'm going to talk about is the motivation of leveraging MEC for in use cases such as teleoperation, and then it will be followed by our actual implementation of the system deployed on a test bed that we have at IIT Delhi only. Then I'll discuss some results that have emerged from those experiments that we have done on the test bed, and finally I will talk about the future scope of such a research. All right, let's get started. So a robot's interaction with its environment can have diverse modalities. It can be broadly classified into assistive or autonomous phases. So in an assistive environment, what is essentially done is that there is a human controller that is trying to control the state of the robot that's interacting with this environment. And in response to which, the human controller receives some kind of a feedback from the environment, obviously, that the robot is interacting with. The feedback itself can have various modes. It can have vision, auditory, let's say temperature sensing, or and it depends on the particular use case that we are looking into. So based on these kinds of feedback that the human controller receives, it takes a preactive, or should I say an assistive action in order to control the state of the robot. Next, these kinds of applications obviously require a timely control and coordination, right? Let's say in critical use cases such as telesurgery or something. Now, I'm sure that you would have seen this kind of a triangle that 5G envisages various kinds of use cases in order to tackle such use cases. But the problem here is that not only do these applications require low latency, but there might be some events, or should we say unwanted events, that happen during the course of operation of the robot. Let's say an object that it's holding falls off from the grip, right? The part that needs to be cut from the body is cut more, should not be done, right? So those kinds of events, what we call as unwanted events, should be tackled in a timely fashion. Now, if that feedback goes all the way over to the controller and the controller sees that and takes the action in response to that event, the round trip time might not be sufficient. So the URLLC component of the 5G may not be sufficient to meet such applications. And that means that we need to entail something else, something more on this setup that enables handling such events of interest. I think this is, yeah. So in a traditional scenario, the human controller sends the signals, receives feedback, and takes that action, what we refer to as a move and wait model. 3GPP specifies three orientations to meet to cater such events. One is obviously related to the split control. The control itself that till now vested in the hands of the human controller is split from it and taken away from it and placed somewhere else. Now the control essentially involves handling the robot itself. The second orientation is distributed learning, and the third orientation is federated learning. Now I'm going to be specifically focused in the split control paradigm, which necessarily entails that the control be split from the human controller. In split control paradigm, the scenario is such that the human controller itself stays at somewhere, right, and then tries to control the state of the robot, but essentially there is an edge server that stays close to the robot itself. The hypothesis here is that the robot itself does not have enough compute. So when and if that kind of an event happens, what we refer to as an unwanted event, the signals that are relayed to the human controller also are relayed to the edge server, and it tackles those events. So now I'm going to be talking about a real world use case that comes from a research done recently in China, wherein they experimentally verified their setup of this teleoperation encompassing 6 hospitals. So there was one hospital where the human controller stayed, and it would do a remote surgery kind of a use case. So this is what their setup looked like. The human controller relays its data and tries to control the robot, and there is a nurse performing that, looking into the state of the robot if the actions are taken correctly or not. Now, as you would see, that there is a massive amount of types of data that are being relayed. Auditory, images, videos, and all those things. Obviously, monitoring a patient is a difficult task, right? It not only relies on vision, it relies on, let's say, transmitting ECG signals or, EMG signals or so on and so forth. So the second point that I want to talk about is that this data is multimodal, right? So it may have varied bandwidth. Now, a profiling of the time analysis that we do is that it's the 2 hospitals that we have checked here are about 500 kilometers apart, right? And this is the timing framing of that, whatever they do, during that telesurgery. So essentially, when you are trying to, let's say, cut a part of the body, now it will require the movement times, the delay of the channel itself, the waiting time of the human, the activation time of the robot, and so on and so forth, which has been framed in this kind of an equation. On response to which of the control that the human controller sends, it receives a feedback that it needs to process, and based on this, it needs to take some kind of an action. So this kind of an event is expensive. The current ping statistics, I'm sorry, this is not working, I guess. Yeah. So the current ping statistics on the current network paradigm that we have in India tells us that about for 500 kilometers of distance, there is a delay of about 30 to 40 milliseconds, right? And if such kind of a telesurgery use case is done in an incremental way, let's say human sends a signal, it receives feedback, and sends another signal, it receives feedback, this may be too expensive to deal with, right? Yeah, so about that, now what we are trying to do is we will leverage MEC. So there will be an edge server that will stay close to the robot and tackle those events of interest which are unwanted. Yeah. So this was one aspect of this, that there is a latency issue, it needs to be tackled in low latency fashion and all. The second is that the data is multimodal itself. As I said, that it may comprise various types of signals, and various types of signals can have varied bandwidth requirements. So there needs to be an analysis of the edge control paradigm also as to what kind of data should be relayed on the edge to take some kind of an action. So based on these 2 challenges, that 1, we need to have low latency, and 2, we need to tackle high bandwidth data, MEC comes into the picture because it guarantees us a low latency framework. And split control, we can do, obviously we can place some kind of a control on the edge server itself, right? So all these applications, like related to haptics, which involve sensing of the environment, based on sense of touch, right? So those kinds of signals are low latency. They have low latency requirements, but as I said, that some kinds of environment events may need special attention, and that's why leveraging MEC might be a good option here. And in that case, the MEC would take a quick takeover when that event of interest has happened. All right, so our system has these 2 devices. One is the haptic glove, and other is this robotic hand on the left. The human controller sends these control signals to the robot, and it receives haptic signals in response to this. So haptic signals here refer to those signals which essentially involve interpretation of the data that exists in the form of touch when the robot touches some objects in the environment or interacts with the environment. So haptic signals itself might be a composite term. It may involve force signals, it may involve tactile, sensing, and all those things. In this setup, we are using pressure sensors. All right. The system has been integrated with a ROS framework embedded with the 5G testbed. Now, here I want you to look into some aspects. As in the human controller, the devices that are worn by the human controller may not be standardized with respect to what the robots demand. So there might be a change in the degrees of freedom, variation in the degrees of freedom, and we need a mapping function in order to make those robots interact with each other seamlessly. So there needs to be a mapping function, and on top of that mapping function, there needs to be an edge application that needs to be run to cater such unwanted events. Yeah, so we have integrated this setup with the 5G testbed that we have at IIT Delhi. Essentially, edge application that handles those events runs on a host that is intelligently selected by the orchestrator. And on the two endpoints, we have the hardware, the two devices, the two robots that are interacting with each other. Now, the second point that I want to talk about is what kind of data that needs to be relayed on the edge server. Not all data needs to be relayed to the edge server, right? So otherwise, we'll really have to make those edge servers really compute, intensive, right? So here, what we have done is we have tried to characterize the signal and traffic characteristics of that data that's relayed to the human controller. In this case, we have assumed that a robot, whatever it does, eventually acquires a repeated set of events, states that it has to do throughout an entire operation. And we try to realize the traffic rate. Could we compress it? So one of the works that we are doing in our group is we are trying to see what is the net information content in those signals that essentially need to be compressed. Until which we can achieve that kind of a modality where only some part of the data is relayed to the edge server and make it efficient. The other part that we have done is we have defined a term called as edgifiability, which we will discuss by the end of this session. So in a split control paradigm, what is the feasibility of those algorithms that run on the edge application and tackle those events of interest? Obviously, not all the algorithms can be edgifiable, right? Some might be, the processing need of that algorithm might be so large that it overshoots that the latency requirement and becomes unnecessary, right? Okay, so I'll come back to the signal characterization part just after this. Yeah, so as I said that not all the algorithms can be edgifiable, we have taken one such event, which is slip. The object of interest is currently held by the robot, slips off from the grip of the robot. Now, the slip itself has various physical properties, right? So it's governed by the laws of physics. So there is a deterministic, or should I say a limited set of interval wherein that slip should be handled. So in that time gap that we have, we need to essentially put in the processing, whatever the algorithm needs. We need to put in the activation time, and we need to put in the channel delay that it has. So based on all the composure of all those time delays, we need to essentially come up with an algorithm that does the job in that time slot. And yeah, so I would like you to play this video. So this is basically the simulation of the robot that we have in the lab, and it's trying to pick up an object of interest. All right, so upon picking up, this object can either fall or not fall. So here the edge application needs to tackle if and when that event of interest has taken place. All right. So as a breakdown of this process, this entire process can be broken down essentially into three parts. So one is reaching the robot, and other is grasping that object and lifting the object. An analysis was done on the type of force signals that we receive during this entire operation. So as you see that there is some variation in the force signals, obviously when the robots interacts with the environment, and we wanted to see if we can develop an algorithm on top of this where that event of interest can be detected and be edgifiable at the same time. So yeah, so the time slot, the entire time slot that we have to in order to detect that slip can be broken into processing delays, algorithmic delay, and channel delay, and so on and so forth. And wherein the pink suggests that the pose has been detected, and the pose has been marked in response to that slip, and that slip can be prevented. All right. Now the interesting result that we have got from here is that let's say you are sending that robot to Jupiter where the gravity itself is very, very huge. So we try to map this event in terms of the characteristics of the event itself. So this is a plot between the time slot that we have available in order to tackle that event with respect to acceleration due to gravity. So what you see is in the red part, when the gravity increases, your edgifiable algorithm essentially becomes irrelevant there. So not only do we need to make our algorithms efficient in terms of the processing, in terms of the communication delay, we also need to make them effective so much so that they be able to tackle that event of interest. Right. Okay, so I'll take a few more minutes. Regarding the signal characterization, so the robot was able to define its states in terms of a repeated set of events. And we characterized the information content in this robot as a measure of entropy per sample. And we tried to see if we can compress this signal. So as you are seeing in this graph, the signal that is sampled from 1 to 333 hertz, and we could see that after 128 frequency, the information content almost remains stagnant, right? So that gives us a pointer that this content can be compressed to some degrees. The robot gives us data at 333 hertz, and we could see that after 120 hertz, the data becomes stagnant, and we could compress the signal at this level. And effectively, when the information content could be compressed, the data rate itself could be compressed. So here, this gives us a notion that not all the data needs to be relayed to the edge server. Only a specific portion of the data needs to be relayed to the edge server. So using these inferences that only some data needs to be relayed, the edge is very close to the robot itself, and that algorithm itself is edgifiable. Based on this, we come with a definition of the edgifiability. Let me read it from the book only. So it's a non-empty set of physical properties when the control algorithm is deployable on the edge and be successful at the same time. So that be it from my side, and I'll take one more minute to discuss the future scope of this. So the other aspects that we are looking into is we are trying to see if we can develop some latency-aware algorithms where we can predict the next step of the robot that it's about to take. And the second thing we'll see that if those signals that we receive can be used to perceive the environment in a low augmentation mode, because we are not using vision or some kind of a high-dimensional data right now. So that will be it from my side. I'll take up questions now. Thank you.
Thank you. One question we'll take.
So you talked about the split spacecraft. So splitting can also, events are not mutually exclusive. It may lead to split brain.
Yes, sir.
What's your comment on that? How would you address that?
So you are saying that, yeah, so this is a good point. So what we essentially came from the results is that we saw that the states of the robot itself, where we are essentially containing those information, let's say, at the joints of the robot, right? So could one finger be predictive of the next finger also? But unfortunately, we did not see results like that. So essentially, you'll have to send all the information about, in this case, obviously, and it will be use case dependent. So let's say in surgery or something, the results might be different from just say vanilla, let's say picking up a cube or those things. I hope that answers your question.
Essentially, to extend, we need to make sure that they are mutually exclusive. Otherwise, the split can cause.
I know, sir, but it's not necessary. Yeah, so it's not necessary that they are mutually exclusive. Yeah, thanks.
Okay, so thank you, Munib. This concludes we conclude the session right here. That's it. Yeah. Thank you.
Thank you, sir. Thank you, all the speakers. starting the session in another 5 minutes. Good afternoon, everyone. Our last session of the day and of this 3-day conference is on network architecture, simulation, and testing of 5G advanced 6G wireless systems. I now invite Professor Radhakrishna Ganti to moderate this session. Professor Radhakrishna Ganti is an associate professor at IIT Madras. He was postdoctoral researcher in wireless networking and communications group at UT Austin from 2009 to 2011. He received his BTech and MTech in EE from IIT Madras and Masters in Applied Mathematics and PhD in EE from the University of Notre Dame in 2009. Thank you. Sir, the floor is yours now.
Good afternoon, everyone. Thank you for coming here. Welcome to the last session of this conference. So we have an interesting lineup of speakers. Unfortunately, the first speaker, Satish, is unable to come, so we'll start with the second speaker, Mr. Joby George. Joby has been working as the director of Keysight R&D, responsible for protocol carrier acceptance. He has vast experience in telecom. I mean, he has started all the way from 2G and he has been building products on various test and measurement equipment till 5G. I mean, I have been interacting with him for 5GI. He's a great technical person. He leads about 100+ team of R&D people in Keysight. I mean, you understand Keysight builds the first the protocol testers which others use to validate their products. So they are experts in understanding guessing what the next generation technologies are. I mean, they have a better roadmap than most of the other people. So I welcome Joby George to give his talk on what 6G is going to be about. Thank you.
Thank you. Good afternoon. As Professor has already introduced myself, so thank you. I jump into the agenda. Okay, let me see whether this is working. What is that? Okay, thank you. Okay. So, as we moved from 2G to 5G, we have moved ourselves connecting people to connecting things. And the vision of 6G, some are saying that it will be connecting intelligence. So we are going to talk more about that. And in the 5G, to achieve the vision of 5G, we have changed the radio technology. We have added more spectrum radio frequencies, and more use cases came in. In 6G also, we expect similar thing to happen. So all these technologies will change. In this presentation, what I'm I'm sorry. Where to? Oh, you got to slow down. Right, okay. So the next slide, right? It's not moving. Yeah, got it. Thank you. Sorry for the trouble. So, in this paper, I am going to talk more about the contribution of these enabling technologies in 6G. Then we will also go into some of the key developments and test challenges and how Keysight kind of companies and professors, test beds, how it can help overcome these challenges also. So I am trying to explain, so you would have seen the 6G use cases in various ways. It is a representation of my own understanding. Okay, it is a different way. I am trying to make it very simple so that you will understand, and so that this can be used by, you can go explore and study more. Okay, thank you. So this is one of the slides I have borrowed from my CEO. So we believe in Keysight that we are still, the 5G is not at over. So we are talking about 6G now, but 5G is in the advanced stage. We still need to go into the next levels. Like we are only talking about the enhanced mobile broadband. We achieved just now that. And in the release 16, release 17, we are going to have more of technology. So we are going to talk about that. And then network transformation, like disintegration of the network, cloudification of the network. This is already helped us. Maybe many of the small players come in different components, and the interface is also well defined now with ORAN. So that is also happening. And now we are going to jump into 6G. It's a quantum leap we are going to take. So I'll just go through some of the use cases in 6G to explain it better. And then we'll go to what is the technology. So in 5G, there are three vectors. We have already spoke about, many of the presenters would have already talked to you about this. EMBB, that is the enhanced mobile broadband, to achieve the data throughput. That's all. We have already done that. And the next one is the ultra reliability and low latency. So this is something which we are working on now. I think release 16 and 17 has some specs on that. We are working on that now. And the massive machine-to-machine type communication. So that is another one which we are expecting, but this is going to be on LTE technology mostly. So in 5G advanced, we are going to have more verticals added into that. So like NSN, that is the TSN, that is the time-sensitive network, which is related to the URLLC. And then the reduced capabilities, that is more of the MMTC related. And then NTN is about the coverage, like non-terrestrial network. Like you will use the low orbit satellite to communicate it as a node B, that way. And then on top of that, you will also use artificial intelligence as a service. So in 5G, you will not see that it is using for the network. But, and you have also seen, in 6G, many triangles, many ways people are representing. This is another way of mind. Okay, so this here, what I have done is I have taken out the sides a bit. So in 6G, the main thing is we are going to continue enhancing our these three vectors which were in 5G. And then additionally, we are going to add a few more, 3 more vectors in this. So I simplified it like sensing. Why sensing is? Because we are going to use sub-terahertz frequency in 5G. I will come to that spectrum later. But then this frequency has that feature that you can also sense. So you can sense the space around you, your environment, and you can control based on that. Sensing is going to be one key vector. And the other one is low energy. So we all know that the current network, which is very power hungry, And low energy is about sustainability. Like we need to reduce the overall energy usage. And the third one is about ubiquity. Ubiquity is nothing but the coverage plus the security. So everywhere you have coverage, everywhere you have security. So you connect to the network anywhere and you get full security also. This is what. And then on top of this, this is on the same plane. And we are going to see this on next plane. So we are going to apply AI in all of this. So we are going to next levels. So all of this, we are going to apply artificial intelligence, learning algorithms. So we are going to work on that. This is what my model of the 6G. So half partially taken from Ericsson and added my own thinking into this. Thank you. So the next one, I'm going to the use cases a bit more. So we know, the first one is about enhanced human communication. How we are going to enhance the human communication. So what we are doing in the current mobile. So this is, we are in the human world. So whatever we are in now. And in the human world and digital world. So the overlapping of the digital world and human world is going to be more stronger in 6G. Why? The communication is going to be more stronger with the added sensors into that. So like currently, the sensors, currently we can see that hearing and speech, hearing, all those things we can do that now, touch, seeing. But additional to that, smell, taste, all of that things will be coming into the this human world, means communication. So this is, we call it as the immersive communication. So 6G immersive communication. So this is what about human world and the digital world merging. And this is not revolution. It's kind of an evolution. You have seen that in 2G also we were doing audio. In 3G we did our data and then video part a bit. We could not upload, we could download. But in the next in 4G and all, we have seen the location added to that, and you have seen along with that our web technology is also evolved. Then we could able to chat, we could do reels, how we could make this possible, right? So and these all are evolving. So if you see from 2G to 6G, this will be the human and the digital world will be interacting more. Okay, so I think I'll go a little fast. So main thing in 6G will be the haptic information, that the sensors feedback we are going to get, and in 6G you will be seeing a football match as if like a referee seeing or a player seeing in the match in the field. So this is what going to be changing, and the holographic image. So holographic image, you definitely need 1 terabit per second. So means like for a, I think it is about 24 bits of color, 50 bps of frame per second. So then you come to that extrapolate, you will get 1 terabits per second. You need for a full image of a person 180 centimeter to be projected. So that is what the speed you need, yeah, in the 6G. Sorry. The other use case is about enhanced machine communication. So we all know that the factory, the industry 4.0, we are already having the machines which are controllable, but non-real-time controllable. Now this is going to be changing with the real-time control, with sensing, control added to that. And this is what the digital twinning. So like you can create a digital image of the machine in the physical machine in a digital world, and you can control it. That is what it is. So it is about the current robots. Robots will be changed to cobots, the collaborative robots, which you can take your controls real time and act on it. So if you see that, I'm just going in little detail on that. Currently, the world, on that physical world, is two different parts, like IT and OT. Information technology and operational technology. Like information technology is non-real time. You can control, but it's not real time. OT is on the floor, on the shop. So you are controlling it. So this is two different worlds currently. So this is going to be merging in with the help of artificial intelligence. You will be controlling. So as I mentioned, the robots, currently the robots will change to cobots. And then it will be like, at the moment it's working independently, autonomously. Now it will be working with your control real time. Okay. So another use case is all these things working together, and we are adding some services to it. I am taking one of the example of services. Many examples are there. One of the example is digital events, a healthcare center. So here you can have transportation, you can have any other cases also, agriculture, you can add. But here, in human world, you will be sensing your vitals, and that will be stored in a server in a cloud, and then artificial intelligence used to determine whether you are well or not, and then inform the physical world, machines working on that. All those things is possible. It's an interaction of all of this. It's kind of overlapping all this world together. So we are getting with this all, we are getting a case. So we are also going to add AI and the security to this. So with this, we are getting a clear definition that connecting intelligence everywhere and interfacing, interacting with human, physical, and digital world. This is what the definition of 6G. Okay, so now let us move into the time scales. What is the roadmap? What we are expecting this to happen? So you all know that World Radio Congress that is going to happen in 23. We expect that the spectrum required, which will be released. So this is also, and along with that, ITU's vision is also happening. At the moment, the ITU's vision is happening. In the case, vision in the sense use cases are developed. That's what happening. So that's what the use case development time. We are going to get the spectrum also. And then we are going to work on the 3GPP is the SDO, Standard Development Body. So they are going to work on this study item and then a work item. We expect by release 20, the study item will happen for 6G, and release 21, the work item. So it might be, we are talking about somewhere 26 and 27 time frame. And by 2030, we might have 6G realized in the world. Yeah, this is what we expect in the roadmap. And then so it is all not happening alone. You cannot work alone. So this mobile technology is happening. We know that 6G is having use cases I have already mentioned, but the web also, internet also changing. So internet 3.0 is going to come. So 3.0 is also talking about the same language, whatever we are expecting. So, and industry 4.0 is also aligned. So that way we can say that all of this, like native AI, trust, and sustainability, merging of this human, physical, and digital worlds, all of this we all talk, some are saying this as metaverse. So this is the metaverse, what we are talking about. So now so now we'll just go into the spectrum. So spectrum allocation, how it is going to happen. So you know that 5G, we have FR1, that is the up to 6 gigahertz frequency, and then FR2, that is millimeter wave, that is from 24 to 48 is already there, and then remaining is also maybe allocated now. So that is the 5G spectrum. But 6G, it is not only going to use a high band, but we are going to reuse that existing bands also. That's what it is. 6G is going to use most of these bands. Okay, low, mid, and high bands. And as a WRC, okay, sorry. Yeah, I think a little more. Yeah. Okay, fine, thank you. So that is what the WRC is also doing the harmonization and getting the spectrum available. So these all are the, we are going to get. So if you see, we are going to have at least up to 250, yeah, 250 gigahertz of frequency in the 6G. That's what we are expecting. And you can see that the sensing capabilities are there in that area. So you can use that sensing capabilities over there. Okay. So then on the technology front, so this is from the European EXA project, and then Huawei's white paper, the technology. So there are 6 pillars in the 6G technology. So I think many of you have already seen this. So artificial intelligence is one important thing. Artificial intelligence will be used for the network, and as artificial intelligence are used as services also. Like for the network means network optimization, channel, all those, like any decisions making for the network to optimize, that thereby we can also reduce the overall usage of the power and optimize the network. That is possible with AI. And then AI as a service, we are seeing many of the other services. We are already in 5G, that is also there. And network sensing, I have already talked about. Extreme connectivity is going to be the data rate. It is like 1 terabit need. And then integrated NTN. It's more than the NTN what we are talking in 5G. It will be integrated NTN. Like it will be like more commonly used in 6G. And security is one major aspect. That's why, and sustainability. So this is what making us to connect everywhere and is with a secured way. So native trustworthiness is what important in this. So I'm just explaining about one use case, the first one, the immersive communication with this technology front. So if you can see, you need millimeter level imaging for holographic picture or centimeter level localization, and we are going to increase the number of devices density. I think latency also need to be very less. So these technologies are going to use for achieving those use case. That's what it is. So now we go into, I think there are many challenges in this. Okay, so many of the speakers in the morning also, they talk about many challenges. So one of the challenging area is this sub-terahertz, how we are going to test it. So how we are going to, I think, develop it and test it. So at the moment we don't have semiconductors also you can use for generating or testing this frequency. So transceiver testing, semiconductor testing, antenna testing and all going to be really challenging. In 5G also we have seen that millimeter wave, the path loss was very high and we had to use high gain antennas and all. So that's the way now how our link budgeting in the sub-terahertz is going to happen. And another thing is the accuracy part. If you see a small movement in the sub-terahertz, like 1 degree you want to change, it is almost like 3 micron accuracy. It's like 1/20th of your hair. So how precisely you will change the 1 degree? So that is what very difficult. And how can you make the chambers like this low cost to achieve that kind of precision? So this is what the challenges in the industry now. And other one, I'm just taking one of the example is the artificial intelligence usage. So you all know that, yeah, channel state indicator in 5G. You know that it will be informed to the device, and device has a fixed algorithm which determines what is best, and it will communicate back to the network. Simple example, but when it comes to 6G, this deterministic algorithm, the fixed algorithm is going to change for learning algorithm. So now learning algorithm is used. How you will train with the data. So, and where is the data available, and what kind of data you need to use for training, and how much of data is sufficient? Is it 1 is sufficient, 10 is sufficient, 10,000 might be more. So we need to find a balance on that. And that way it is like and again, testing is a big challenge. Like in a deterministic algorithm, you know that pass is always pass, and in fail is always fail, right? But in the case of AI is used, then you cannot say that fail is always fail, because you wouldn't have trained that AI in well, right? You don't know that. That's what the challenges we are going to face in industry. So that's all for my presentation. And we have learned some of the 5G, 6G introduction, use cases, timelines, technology and test challenges. Hope it was useful. Thank you.
Thank you. We have time for a couple of questions. Anyone?
Okay, then thank you. Thank you very much.
Look, I have one question.
Sorry, thank you.
So the terahertz are actually being used by physicists right now.
Yes, yes.
The test equipment is readily available as of now. As you said, we don't have ABC way of generation.
Yes.
When do you think that the academic institution and all that will be geared towards starting this terahertz?
I think the study is already started, because we already know that World Radio Congress is going to release this, and we need to use, and as Sarah is already mentioned, we use this sub-terahertz for even now today for measuring the quality of the vegetables, sorting algorithm, sorting and all. So we are still using. But when we are going to apply that into the communication field, we need much more things, right? So that is what. So the study is already going on. So if you see, even Keysight also involved with many of the organizations and started on that kind of R&D. Thanks, sir. Yeah, it will be initially. It will not be. We are not going to jump into sub-terahertz phase. So we will be like using the already existing low bands and mid bands, and then we will be going into the next levels. Thank you, sir.
Thank you. Please give a hand of applause.
So our next speaker is Mr. Suresh V from CDAC. Mr. Suresh has been working in CDAC Pune as an associate director. He works in the area of smart cities, IoT, M2M, and with applications to healthcare, heritage, transportation, and human-centric device. He has about 22 years experience in software development and leadership, and many leadership. He has played many leadership roles. Prior this, during his prior tenure at CDOT Bangalore as a team leader and a research engineer, he was associated with cutting-edge telecom product development and application-oriented research. He is involved in projects of national importance, working groups, and standardization bodies and technical forums. So we welcome you, sir. Please deliver your talk on 5G simulation platform for healthcare application. Thank you.
Okay. Okay. Okay? Yeah. Thank you.
Good afternoon, all. Would you like to play the video? I'd like to just share one short video as a precursor.
With the increased use of digital records in healthcare, medical images are also being captured, stored and transferred using various health informatics solutions. These images play a crucial role in diagnosis and treatment. As specialists like radiologists, imaging pathologists and dermatologists are an integral part of diagnosis and treatment, clinicians may need to discuss the medical images with the specialists for complex cases which require an easy-to-use, real-time collaboration solution for medical images. CDAC presents Collab Med Imaging, a real-time collaboration service for medical images. Working towards the Digital India mission, CDAC has developed this solution using the latest technologies that connect remote physicians with specialists to discuss cases through medical images. A typical workflow in Collab Med Imaging involves easy steps such as the clinician schedules the event with a team. Once the session starts, the clinician securely shares the medical images with other participants. They discuss clinical conditions by marking and sharing annotations and imaging operations. Rendering of these operations is always in real time and in sync with audio-video. These updated images can be saved for future reference. The solution supports DICOM images with other image formats. Collab Med Imaging can be used for continuous medical education and training programs to improve learning experiences. The modular nature of Collab Med Imaging allows it to be used as a standalone solution as well as a plug-and-play feature of any other medical software. It leverages the high bandwidth and low latency provided by the 5G network to make a rich and smooth user experience even with large medical images. The solution is optimized in CDAC's own 5G lab and CWIT IIT Madras 5G testbed. Collab Med Imaging is an award-winning solution from the 5G Hackathon organized by the Department of Telecom, Government of India. The solution's versatility makes it useful in other domains as well, such as space, agriculture, education and bioinformatics, among other areas where discussion over images is required. The solution is already tried, tested and commercially available for immediate deployment. We gratefully acknowledge the support received from the Government of India.
Thank you. Can I have the slides? Yeah. So I'm Suresh. I am from CDAC, and just to set the stage, I have showed this video and displayed the video, and this is one of the applications that we are trying to see that how it will function on, or rather, if you board it on 5G, how it will go. So that's what some of the features. With this as a stage, I would like to take you through our presentation on and our experience basically on 5G simulation and applications. So to start with, CDAC, Center for Development of Advanced Computing, came into existence because we were denied supercomputer by Cray, US, America, the United States of America denied us supercomputer. So our engineers were tasked, 1988, the confidence of the leaders, they gave them a task to come up with our own supercomputer. That's how we are here with 12 centers across India. And we are with a range of verticals. You talk about the multilingual or power electronics or healthcare and IoT, 5G, AI. We have now all centers, different centers working in different areas, and we have proven technologies and deployments of various applications and services for all these years is primarily to take the IT for the masses. So that is with the one goal, so that to bring the benefits of IT for socio-economic development and human advancements. That's our mission. So with this as a stage, what we are here right now is, I have to just get used to it. Yeah. So I am going to talk mainly about healthcare. Of course, I will touch upon a couple of other applications, potential application which we are trying out for 5G. So the main thing of this, all our applications you see, it's time tested, almost 23 years of journey in the area of healthcare. So again, it is not one center or one head. It is all, it's all across India, different centers have worked in different area, and again, it's all based on need, and again, based on some of the innovations at that time, at that point in time. So different applications came into existence. So the main challenge for us is that, the main challenge is that I'm not able to see I have to look like this because I'm not able to see that very close. Is that fine? I'll try to see this. So the main advantage is that we cover both, whether you talk about urban or rural mass. So that was the focus, and specifically keeping the healthcare needs in the system. So all these products, many of these products came into existence when people, it is on the need basis, and also the medical fraternity, what they want. So with the discussions ranging from, again, private or mostly government hospitals and different medical experts, with them in discussion, we have came with a range of the products and services. Now, the main thing is what we, in this particular discussion, what we are going to have is, so just to, in the interest of time, we have not displayed a video of eSanjeevani. So you can Google or YouTube, you can see this. eSanjeevani is one of the de facto telemedicine solution which is available with CDAC. And if you see the statistics, it is almost more than 6 crores, if I'm right. So more than 6 crores consultation. And also we have eSanjeevani up and running in different healthcare centers, which is 90% of these healthcare centers are rural area, where we have our own challenges of network and various things. And it's all bringing the healthcare advantage to the remote and the rural mass. So that's how CDAC brought all this solution. And it is also enabled with accessibility, where a blind or different accessibility issues and differently able people can seamlessly through this, go through this and have a consultation with a medical doctor, even from the remotest part of India. So the idea is this, that this is one more, this is what you saw, Collab Medical Imaging is one of the plug-and-play solution as a part of a larger umbrella, which is an integrated telemedicine service over cloud. This is again one more product with a different flavors in that. So this is, so mainly few applications, what we did is, the challenge before us was this, all these applications are matured, up and running, and some are in this maintenance. When 5G came into picture, the main thought for us was, how do we make it 5G ready? What are the things that we should consider other than whether you profile application for its own performance and those things? How do we leverage the 5G offerings, whether you call it as enhanced broadband or you call it as a low latency and ultra reliability, or on healthcare if you talk about the Internet of Medical Things. So how do we leverage all these things and truly make it a 5G aware or truly make it a 5G enabled application? Say, for example, I just wanted to tell that I talk about technology, but myself, I don't use technology. I was very skeptical in using smartphone. So, but COVID forced me for various smartphone and applications, and without which I was not allowed into many premises. And there are times I faced difficulty where I went to vegetable shop, vegetable vendor, and he didn't allow me to buy because I didn't have a Paytm or GPay. So such issues came where I was forced to take some of the technological advantages because it is becoming more and more necessity than a luxury. So the idea about this 5G applications is that it is not, when we say 5G ready applications, is that the 23 years of journey which I was talking about, it is not that these applications can survive in silo. It simply cannot be. So we have to study what are the requirements or what are the functionalities that 5G offers to us, and based on that, see how we can customize or fine-tune our 5G applications, 5G ready applications. So the main thing is that the application, if it has to take the full potential of the underlying 5G communications or upcoming advanced communication, whether it's 5G plus or 6G or 7G, whatsoever it is, we have to try to see that how we and which are the things that inside this particular telemedical applications, what are the features that can truly leverage the 5G offerings. That's how the challenge was for us. And again, the challenge is this, that we need to equip not only the technical aspects of that, and also the medical practitioners and also the leaders in the medical domain space, and make them comfortable, with the technologies which is providing, and also give them the reliability, that give them the confidence with which they can perform. Until then, we will not be able to make this happen in the from the lab to land. So this mainly I was talking about this large image. That's what the CollabMed was talking about. If a medical expert has a large medical image, it can be a CT scan or some kind of imaging solution, which he has to, in a real time, he has to interact with a specialist in a remote area, and also annotate on that and discuss various medical related things in real time, which needs more of synchronization, transfer of large, sometimes it is a gigapixel images. They have to transfer and then discuss, and all it has to happen sometimes just before the surgery or operation or whatsoever they have to do. They have to do some kind of planning. And this is not possible unless it is supported by underlying 5G technologies. So that's how this application we try to do in our own in-premises, in-house also. And then we try to move it, as you saw in the video, that we also try to do along with a discussion with the larger 5G ecosystem providers, and also the test bed which IITs, and especially we would like to thank CVIT also, because we were able to, during COVID, we were able to start our discussion with them. It was the first experience for us to go and see what it means, 5G, and how the things can be taken forward. That's how this. And this is one of other application which is called voice-enabled doctor desk, and this is again deployed more than 100+ deployments, and there is a plan to scale up to even up to 600 deployments in the coming days. And remote healthcare centers are having this. So one of the key features is that it has a medical speech-to-text, where some of the consultation or e-prescriptions that you can give, where doctors can dictate. Doctors are known for their handwriting. So it's very difficult to capture their e-prescriptions or sort of thing in their whatever they write. So here, when he speaks, a lot of medical terminologies are converted in a prescription format, and it is all mobile based, and also there is a web version for that. And this ASR, what we call it, is also have some kind of, we are proceeding towards patent for this. And this is also another application that we are actively seeing that how it can be taken board on 5G. So in this, again, few things which we did is that how this API integration can happen, how content caching, and some of the 5G offerings which in Android right now which is available, which we try to see that if it is on 5G network, what features we can enable. If it is not, what features we can disable and use in a different kind of, so that to make the both doctor and patient consultation smooth. So those kind of tuning, fine tuning we have done, so that this application, when it comes on board on 5G, which we are trying to do in testing on test bed, and then going ahead on 5G trials, and then going on 5G deployment. So which we are trying to do this. So this application is also actively being tested on CVIT also we are trying to do. So what are the key things that we are focusing on? Now when we talk about this, we are calling, the challenge was this: every time we were not able to go to the external or a third party and try to do some kind of testing in their lab, which is a full-fledged environment they have, where 5G core and your RAN and your user equipments are there. But what we need is that a small emulated or a simulated platform in which we will start isolating different parts of 5G, whether it's only on 5G core or include RAN along with it, or have an end-to-end UEs, and then test in different scenarios. We need to see how the application functions. So that's how we try to have our own simulated environment in-house. Our team, they are here with us. So they also try to go through some of the open source and which is available. And with that, we were able to successfully enable a small setup within our premises with a 5G core and simulated RAN and UE. And on that, we need to do some of these things like quality of experience ultimately we need a quality of experience, whether the medical practitioner or some of the medical providers, healthcare providers, and also patient, how they will experience the ultimate thing with all these things in this, whether a real-time peer synchronization, this is between the medical experts, and HD video conferencing. In some cases, you need that because dermatologists, skin specialists in various places, suddenly, while they are speaking, doctors observe more of the patient's features and the emotions, and also if they have to share some of the things live, they should have a clear visibility as though they are in person. So that's how HD video conferencing. And now in our ITSC, Integrated Telemedicine, we also have a VR medical education, wherein doctors can have a more kind of understanding with AR, VR enabled educational videos in that, which will help them and to, especially the trainees and those people can really see how this technology can benefit. And all this needs EMBB sort of slice, and we need to test that on such a slice. So what we did is that we tried to create a underlying network which gives that much bandwidth so that we can see how it functions before we actually onboard it on 5G. Other than this medical image also, we talked about it. And this is our simulation setup. So CDAC is having our own, as I said, that CDAC comes because of a supercomputing facility. So our own Param Shavak, or supercomputing in a box we call it. On that we have, as I shared, that 5G core and simulated RAN and all these things we have set up. And not only healthcare, we are also proceeding towards transportation and also disaster management and industrial IoT, such aspects. Yeah, 5 minutes. Okay, I'll just. See, the main idea is I'll just quickly wrap up, and maybe I will ask my colleague to come and just share 2 minutes of his experience in that, as I took permission from the chair. So the main idea is that how do we actually see this 3GPP standards based test beds on which how do we run our applications, and then see that the requirements which this application demands are synergized or bring this on board with the stakeholders who are whether it's developers or regulatories or telecom providers and also medical experts. Bring them on board and then see that how do we see this healthcare requirements and the emergencies, not only emergency scenario, even somebody was saying that even telemedicine is not necessary that it's not an emergency situation. Okay, even telemedicine should be in such a position to support any critical, address any critical healthcare solutions, healthcare situations. So that's how we are trying to see that. Maybe I'll just quickly go through this. I would like Pradeep to talk about it on quickly. This is our setup, how these applications are hosted and how this testing which we did. Maybe I'll quickly close with this particular slide. This is our V2X. I will not go into that. In this also, how this in our stall, if you come, we will explain more in detail how vehicular-based emergency situations and also medical-related things can be associated in a V2X, cellular V2X context. I'll close with this before that, before Pradeep comes. So what do I want to conclude here? I want to conclude with 5G must be more than just an underlying communication system. And in order to realize full potential, we need to understand the features and also bring both the boundary of application, whether it's a healthcare or a forest fire or a different kind of application, that vertical's boundary should be pushed towards the 5G boundary and see that how they both gel well with, so that we can provide a good user experience. And 5G supported techniques and tools in a relevant given domain should be more explored in it. And then in a kingdom of 5G, nothing is in silo. We cannot deliver solution or a service if it is a standalone application. It has to be married with a 5G ecosystem or any other kind of communication system. And lastly, to have a seamless interoperability integration with other associated, it's not only healthcare domain separately, whether it's a V2X and different kind of, for example, with the TSDSI on board, with new NIPs which we are trying to do, have a clear API which interacts with different ambulance aggregators and also healthcare providers, and see that in ambulance when it takes a serious emergency condition, and see in that time can they interact with the API in a low latency mode and see which healthcare provider will be more suitable for such kind of emergency situation. That also we do. And with it I will close, but 2 minutes because Pradeep will be able to help you in much more details about this. In a short he will explain.
Hello all. Mr. Suresh has given a good explanation about all our applications. These are all very time crucial and data intense applications. So these are all very good use cases for 5G offering. So we give it to me. Yes. This is the simplified architecture of our testbed platform. The top right, the very first one is the CDAC data center, in which all our application servers are hosted on it. It's a cloud platform. So the very next layer is the SDN orchestrator, which will enable the connection through UPF between my standalone 5G core with the data network, so that the applications will be accessed through the standalone 5G core. The next layer is the simulated version of G-Node B and the UE client, through which the user will come and access the services through 5G core of application hosted on the data center. So this is the typical architecture. So I'll take you through the detailed view of it. Yeah, here you can see the right side block is the one which has hosted all the CDAX application, and the second layer is the network SDN orchestration layer, which will have which is integrated with a lot of open telemetry tools, so that it will understand what is the congestion at a given any point of time. And the orchestration layer will have indirect link to the client side, so that it will tell depending on the feature that was enabled by the client, it will inform what is the slice needed by the application at that point of time. So this is how the client will negotiate with the RAN, and RAN will allocate the slice, and it will negotiate the QoS will be permitted or not, and accordingly the slice will be allocated to the UE. So this is how it works. Yeah, this is one example of our application, how we hosted. You can see the very first one is the HPC cloud platform, where the 5G core and even my data center is hosted on it, so that my application is running on in a HPC mission. And the second layer is the simulated version of RAN, and the third layer is UE stack, in which I have the services hosted by collab-made images were accessible through these UEs. There are, depending on the feature you are enabling by the user, it will, on a real-time manner, it will switch the slice, and it will negotiate with the RAN, and it will try to get seamless connection and enhanced user experience to offer to the end user. So that is the goal of the whole project. Yeah. Any questions?
Any questions from the audience? So what do you think CG should do to enable this healthcare application? Other than just latency and high throughput, what do you think are necessary in CG? I know this is a tough question, but any thoughts on this?
So can you please?
What do you think that 5G should have done better so that this healthcare applications work in a much more seamless manner? Is 5G sufficient? I'm just curious.
No. there are really in healthcare domain very critical applications. I can take the example of robotic surgery or something where a fraction of second latency matters a lot. So in that situations, really like with whatever existing, 4G, 5G, so far whatever the best we have achieved, I don't think they won't suffice the necessary needs of the upcoming applications. So definitely there is a need of upgradation of networking side towards the high bandwidth and low latencies. Yes.
Thank you. I'd like to thank all speakers. So just to add a comment on that, so generally when you work in WAN networks, all of this are collapsible numbers like latency and throughput. Maybe in 6G there may be much more tighter integration at the WAN level because of
AI, the new hype buzzword. I mean, maybe there'll be going to be pilots for healthcare and pilots for something else. We have to wait and see. Our next speaker is Pranav Jha from IIT Mumbai. I mean, I've known Pranav Jha from a long time. He's been very active in standardization, and he's a senior scientist at IIT Mumbai. Has published many research papers, has been in numerous standards activities. He's involved in numerous standards activities, and welcome him to present his vision on the network architecture for 6G.
Yeah, thank you very much for giving me the opportunity to talk to you. I'm really afraid to talk to real people after 3 years almost, when we have been speaking to computer screens. So, pardon me if I make some mistakes or anything. So can we have the slides, please? Yeah. So does this work, or can you? Yeah. No, you can actually change the slides when I request you. That's better, I think. It doesn't. I don't have too many slides also. So. Yeah. Okay. So we are actually, in our group, we are experimenting with different architectural options. So one of the options that we have experimented with, I'll be talking about that. And so can we go to the next slide, please? Yeah. Yeah, so this is, broadly the agenda for today. So we'll talk about how a user service is enabled in mobile networks in general, so 4G, 5G, all these networks. And then we present a generic service-driven architecture, which can actually be used in future networks, say 6G. And how this service-driven architecture, when we apply it to 5G, how does it look like? So that is how, that is what we will talk about. So can we go to the next slide, please? Yeah. Okay. So, when I talk about user services, you might be familiar with, data connectivity to internet, or, so I've given some examples, like media streaming service, when you download, some streaming media, or mission critical communication, push to talk. These are some of the services that users actually can access through 4G or 5G system. But in addition to these user services, the mobile networks provide some services which we can call as intrinsic services. They are not really obvious to users, but these are services that the mobile networks provide. A very good example of that service is mobility. So when you move, your mobile gets handed over from one base station to another base station. So that's also a service. Now that service, is part of the mobile system or mobile network design. So it inherently supports these services. So we will see that, today, the user services that you see at the top are enabled in a different way than these intrinsic or built-in services. And what we are trying to propose here is to make them, harmonious, or make them utilize the same design pattern for both service, implementation. Can we go to the next slide, please? Yeah. So I have given an example of media streaming service. So there are essentially 3 components, or you can say 3 groups of components. So one is the application provider, which provides this service. The other part is the user, or which has been shown as a user equipment because the user accesses the service through the user equipment, the mobile device. And then there is the 5G system, which enables this connectivity from between the application provider and the user equipment. Now, the 5G system provides the data paths for this service. And in the application provider, you will see there are two parts, application function and application server. Application server is the entity which provides the media, the actual content. But the application function is the entity which talks to the user and exchanges some information like, it authenticates the user or authorizes the user before the user can access. So that's part of called control information exchange or signaling exchange. So this signaling exchange happens prior to your actual data access. So, but the interesting thing is, for 5G network, both are data. So even though the user equipment is initially talking, to the application function for some control information, and then later on it accesses the content, but for 5G network, both are data. And both application function and application server are part of the data network, in the context of 5G system. So that's one thing that you need to keep in mind, and that is what we will take it to the 5G system and 6G, in future. Can we go to the next slide, please? Yeah. Yeah, so quickly, this is another example. It's the same, similar mission critical push to talk, but, it follows the same principle. So I just put two examples here just to share that all the, application services are enabled in the same way. Now, can we go to the next slide, please? Yeah. Yeah. So this is a summary, how these services are enabled. So if you see it, there are three parts. First part is exchange of service requirements between a user and the service provider or application provider. The second part is the service is orchestrator. So, service is orchestrated through the 5G network where the data path is set up and the service, and then the third, the final stage is the delivery of the service. Now, so the delivery of service is via the data bearer. And as I said, the first part is also actually happens through a data bearer in the 5G system. That's the interesting part of it. So can we go to the next slide, please? Yeah. Yeah, so this is a broad abstract architecture that we are proposing. We are saying that a network can be composed of four types of or groups of functions. One is the user plane. Obviously, a user is also a part of it, so there are 5. There is a control plane which sets up the path through the user plane. User plane is responsible for carrying the data. And then there are service functions which actually provide the service. And then there are orchestrators, service orchestrators, which actually collect the information from the UE and asks the control plane to set up the service path. So that is the abstract architecture that we are proposing. Now, can we apply this architecture to 5G system itself or the 6G system itself? Because when you look at the 6G system, it is not like this. So can we go to the next slide, please? Yeah. So this is an example of how, when we apply this architecture, how the 5G system will look like. Now, you have seen, you will see that that's the GNB. It is a modified GNB as per this architecture. So there is a control plane function, GNB-CU-CP, which is now, it is there today. It controls the GNB user plane functions like GNB-CU-UP and GNB-DU. And then a critical part of this GNB-CU-CP is the RRC protocol, which is exchanging control information with the UE. Now, what we are saying is that move that RRC out of it and put it as a service function. And similarly, when you go to the core network, so you have NAS layer, which talks to the UE, again for authentication and authorization and registration and PDU session setup. So we are saying that move that out of control plane from CP of the core network and put it as a service function. And then you have orchestrators like mobility orchestrator, which actually does the handover. So it is, that application of the architecture where we move, so if you look at today, the mobility orchestrator and RRC, both are part of the GNB-CU-CP, and they are not known as mobility orchestrator or RRC server. They are part of the GNU-CP control plane functionality integrated within that. You don't know how they are distributed. But what we are saying is that if we push them out and we make this like this, then the GNB CUCP becomes a very simple function. It is only responsible for setting up the data path or configuring the DUs and CUUPs. Similarly, the core network control plane is also responsible for only setting up the data path through core networks, so the UPF. But these entities which are actually talking to the UE, signaling messages, exchange, that are part of the service function or service orchestrator. So that's the, in nutshell, is the idea. The next slide is the last one, I think we can. Yeah, so this is, what we are saying is that if we apply it to the 6G network, so we'll have all these 4 blocks in addition to the UE. So you have user plane, which carries data. You have user plane control functions, which controls those user plane. And then you have service functions like NAS or RRC, signaling functions, which talk to the UE, collect the information, authorizes them, and all that. And then you have orchestrators like mobility and PDU session and so on. So that's about it. And thank you very much for giving me the opportunity to talk to you. And if you have any questions, I'll be happy to answer them.
Any questions from the audience?
Yeah.
How will this affect the RAM?
It will affect the RAM because GNB CUCP now is disaggregated further. So you have mobility manager not as part of the GNB CPU, which is right now as part of the RRM of GNB CUCP, but it is part of an orchestrator which is sitting outside the GNB CUCP. Similarly, the RRC, which talks to the UE, the RRC layer, which moves out of, especially the UE part, the talking to the one which talks to the UE, that moves out of the GNB CUCP. So in the GNB CUCP, you just have DU and CU configuration. The F1 protocol becomes simpler. It doesn't have to carry RRC messages. So basically, signaling becomes just like another data. So what we are saying is that signaling doesn't have to be treated separately. It can be treated just as any other data. If you look at radio, it actually happens. SRBs are not much different from DRBs. So what we are saying is that why not treat SRB just as any other DRB with a specific cost requirement?
Thank you. Let's thank the speaker.
Okay, thank you.
So this comes to the end of the session. Thank you.
Thank you, Pranav sir. May I now request Professor Bhaskar Ramamurthy to kindly felicitate Professor Ganti with a small memento as a token of our appreciation. Thank you, Professor Ganti. Now I'd like to request Professor Bhaskar to give the closing remarks of the conference.
So that brings us to the end of this two-day conference spread over 3 calendar days. As I mentioned in the inaugural session, the conference was conceived quite late as academic conferences go. We had conceived of this only about 2 or 3 months, 2 months before the IMC. Somehow, I think it's the first time there's a semi-academic or almost academic type of research conference as part of IMC. So the idea must have come late to the DOT, and then they asked us if it's possible. So we somehow said we'll do our best and we'll try to pull it off. And I'm really grateful to all those who participated, all the speakers, all those who sent in abstracts, and the committees who reviewed them at short notice. And the program finally looked quite good, much better than what some of us anticipated. And finally, really the big kudos to all the speakers, because out of the 34 abstracts and 3 keynotes that we scheduled, all except one have turned up, have been presented, and only 4 presentations were made pre-recorded. Everybody else actually came here, which I think shows everybody's hungry to physically participate also after all these years. But at such short notice, we didn't see saw very few people excusing themselves for good reasons, probably saying they're not able to come. So really, I'm thankful to all the speakers. I think the participation even in the last session is quite good. So I hope this is a harbinger that future IMCs can also have a parallel semi-academic or almost academic conference focused on research which is a little further down the road, not worrying too much about implementations and standards and all at the moment. And I again want to reiterate the gratitude that we have for the staff at TSDSI, Bindu, Shefali, Sonia and Anupam, because we leaned on them heavily to pull this off in this short period. I think right from creating the web portal to receiving the abstracts to getting the technical committee to, arranging for the technical program committee to look at them, communicate with the speakers, everything. And then the brochure and the organizing here, the being here right through the sessions, making sure everything goes like clockwork. I think I request all of you to give them a big hand. Okay. So, this TSDSI is also a fairly young organization. It's just going to celebrate 10 years next January. It's come a long way. It's doing wonderful work, and it's because of people like them. So thank you very much, and I hope you enjoyed this this conference in this IMC. IMC is of course going to go on till tomorrow evening. So wish you many more productive hours at the Congress, and hope to see you all again next year. Thank you.
Professor Bhaskar, thank you very much for giving TSDSI the opportunity of helping organize this conference. And like you said, we do hope that this conference will be repeated next year onwards also. I also wanted to invite all the participants for a session by IEEE tomorrow on IoT and M2M. It's more an awareness and education conference that will be run here at IMC on IoT principles and standards and 5G. So please do join us tomorrow also. Apart from that, TSDSI runs an annual flagship conference called TSDSI Tech Deep Dive, which is scheduled from 7th to 10th November this year. And it will have around 10 technical sessions. Please do join us for that session also. It's going to be, it's going to be online. There'll be one hybrid session, which will be covering standards for sustainable development. So hope to see you there. Thank you very much.